Hi everybody, welcome to our video course for geometry. Thank you so much for watching. What we're going to try to do in this course, in addition to whatever published materials you have, in addition to whatever textbook you have, in addition to what other resources you have, we're going to try to give you a little bit of a crash course to give you what the information that you're going to need to do well in this course. So I want to thank you for listening, and I would like to get started. And the way this is going to work is I'm primarily going to work off of this document, which you should have access to. It's a PDF document entitled A Course in Geometry. I very highly recommend that you make use of this document. It's got a lot of plain English lessons about all the geometric issues that we're going to discuss. And from time to time, we're going to go through it. But also what I'm going to, and I may, use other examples as well, but also really primarily what I'm going to do is I'm going to also go through the homeworks. This document, the homeworks that you have in this course, it might be in your course syllabus, it might be in other resources given to you, but either way, you should have these homeworks. Now, what I obviously recommend very, very strongly is that you do these homeworks without my without watching this first, because if you do this homework after watching it, it'll be kind of pointless. It's not really going to help you very much with understanding what you're doing. But after you already do your homeworks, and after you've already, given it your best shot, well, then I would recommend watching this video, because what I'm going to try to do is I'm going to go through the homework and explain how to do all of them. And once we do that, we will, hopefully that'll help you a lot. So, for the first chapter, I'm not really going to go through this first chapter here in this PDF document, the geometry lessons PDF document. And the reason is because this is not really, chapter number 1 is about problem solving in geometry. You don't have to know a tremendous amount of geometry for it. You just have to know a little bit about numbers in general and be able to problem solve a little bit. So let's go ahead and look at the homework. Here's homework number 1. And so let's take a look at some of these questions here. Like I said before, obviously I can't control what you do in terms of watching this, but I really request that you please try to do these on your own first. And if you haven't done it, maybe you can go ahead and pause the recording, and I'll still be here when you get back. And then I will be here to walk you through it. Okay, now that you've paused it and given yourself an opportunity to try to do everything first, let us go ahead and look at homework number 1. Question number 1. Again, these are things that are not really geometry-based in terms of remembering things and remembering formulas and remembering concepts, but it's more like riddles almost. So hopefully these could be fun even. A large cube is formed by arranging 27 smaller white cubes of the same size in a cube shape. 3 faces which share one corner of the cube are painted red. How many of the smaller cubes will have exactly 2 red faces? In other words, the outer corners, the outer edges of one corner of the cube is painted red. How many of the smaller cubes will have exactly 2 faces? Now, a couple of things. First of all, the first thing you need to realize is that a cube in general is a 3-dimensional representation. It's kind of like a 3-dimensional square. And the way you figure out the area or the volume of a cube is it's however wide the cube is multiplied by itself 3 times. In other words, to the 3rd power. 27 is 3 to the 3rd power. So 27 small cubes making up one large cube is 3 by 3 by 3. If you have a bunch of little blocks, if you have 27 blocks, you can try it out. Otherwise, you're going to have to trust me. If you put 3 blocks side by side, pile 3 more on top and 3 more on top, then you're kind of going to have a square of 9 altogether. If you put 2 squares next to each other, 2 more squares of equal size, you're going to have 27 altogether. It's 3 times 3 times 3. So they say 3 faces which share one corner of the larger cube are painted red. Now, the best way to look at this would be to have a Rubik's Cube in front of you. But if you don't have a Rubik's Cube in front of you, you're going to have to deal with my very crude drawing of a 3-dimensional of a three-dimensional cube. Now, again, as you're going to see over and over again in this course, I am not much of an artist, but hopefully this will give you the opportunity to at least see what I'm talking about. So here we have a representation of a cube, like a box, and everything is 3 by 3 by 3. If you count the total number of cubes, you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then another 9 on each level. Another 9 behind that, another 9 behind that, and you have 27 altogether. So the question says that three faces, in other words, 3 of the outside, which share one corner, are painted red. So it doesn't matter which corner it is. It could be any corner. But since this is our drawing, let's call it this corner, this upper corner over here, which means all 3 of these sides are painted red. I'm going to color this red. Here. Let's... Basically, these whole sides, this is going to be drawn red, this whole area. Let me put it in each box just to make it a little easier. This whole side is painted red. I'll put a little red circle in everything that's painted red. This corner is painted red. Okay. In other words, these are all the boxes that have red faces, because the question says that 3 faces which share one corner, the entire faces. Now they ask you how many of these have exactly 2 red faces. Well, the corner ones, this guy's going to have 3. This cube over here, and here I'll change the color, this cube over here is going to have 3. Here, here, and here. So we don't want that one. In terms of how many of them are going to have 2, well, it looks like this one's going to have 2, so that's 1. This one's going to have 2, so that's a second one. It looks like this one's going to have 2, so that's a third one. And it looks like this one's going to have 2, so that's a fourth one. So I only see 4, assuming this whole side, and this whole side are all painted red. I only see 4 smaller cubes that are going to be painted red. So again, this question wasn't really a whole lot about geometry, but it's about visualizing the concept in your mind. Let's take a look at homework number 2. I'm sorry, question number 2 over here. And that is, so I think the answer to that is 4. Again, just to reiterate, if we look at this diagram over here, we're just painting 3 sides red, and looking at how many of these are going to have 2 sides painted. All of these, this one, all these are only going to have 1 side painted red at a time. But I see 4 of them that are going to have 2 sides painted red. Okay, so let us take a look at question number 2. If all the diagonals are drawn in a polygon with 5 sides, a pentagon is a 5-sided polygon. So let's start this by drawing a 5-sided figure. And I'm going to draw 1 side, 2 sides, 3 sides, 4 sides, 5 sides. Okay, that's what a pentagon is, a 5-sided polygon, which means a 5-sided figure. Then they ask, what is the maximum number of intersections of 2 diagonals? This is actually a strangely worded question. I mean, there are more complex formulas to determine the number of possible diagonals. But if you have 2 diagonals, if you have exactly 2 diagonals, diagonal just means from going from one to another, then the maximum number of intersections would actually be just 1. I mean, they could also be 0. For example, if you had that diagonal and you had diagonal means from one side to another, then there'd actually be 0 diagonals, 0 intersections. But if you have exactly 2 diagonals, you could really only have a total of 1. So, I mean, the question, I guess, could be, the way it's worded, it's actually quite easy. Okay, number 3 here. The measure of one angle, and you know what? Well, let's skip number 3 for a minute. And let's go to number 4. Samuel, Martha, James, Katie, and Raphael all go to the movies. James insists on sitting next to the aisle. Samuel and Martha must sit next to each other. Raphael sits next to Samuel and next to James. Who's sitting next to Katie? This is an interesting one. This is actually the kind of thing that you might see on the, on the law school admissions test. It's kind of a riddle here. So let's see how we would figure this one out. Let's see. James insists on sitting at the aisle. So let's draw a little aisle here. And then we've got 5 seats. 1, 2, 3, 4, and 5. Let's work this out. James insists on sitting on the aisle, so we're going to put James here. Samuel and Martha must sit next to each other. And Samuel sits next to, Raphael sits next to Samuel and next to James. So we're going to put Raphael right here. And also we got to put Samuel here because Samuel has to be next to Raphael. And Samuel and Martha must sit next to each other, so we're going to have to put Martha here. And so the only one that's left over here is Katie. So the question is, who sits next to Katie? It's just a matter of drawing it out, and the thing actually becomes very easy. I take it back. This is really too easy for questions on the law school admissions test, which they get a little bit harder. But the only one left, of course, is Martha. Has to be next to Katie. Next, let's look at question 3. Let's do that. We'll do the other questions a little bit later on. So let's do number 3 over here. The measure of one diagonal of a triangle is twice the measure of the second diagonal. The measure of the third angle is 12 degrees more than the measure of the first angle. What is the measure of the largest angle of the triangle? This is actually a little bit of algebra and a little bit of geometry kind of mixed in. So again, let's copy and paste the question. Let's bring our box here. And okay, there we go. So let's draw our triangle here. Okay. Okay. Now, what do we have here? We've got one angle is twice the measure of the second angle. Now, whenever I see, we don't know exactly what the first and second is, but I can express the angles in terms of a variable, in terms of x. If you've taken algebra, you may recall that that's the way you always establish a quantity that you don't know. So I'm going to call one angle x and another angle 2x, because one angle is twice the measure of the second. This one up here is twice the measure of this one down here. The third angle is 12 degrees more than the measure of the first angle. So this was the first angle. So it's x plus 12. So we can establish that we can call all 3 angles x, 2x, and x plus 12. Now, we didn't learn it yet, but I will tell you now, and you may recall this from high school geometry. Every triangle has to equal up to a total of 180 degrees. All the inside angles of a triangle add up to 180 degrees. So if we're doing this like we would, any regular algebraic expression, we would add them all up and they equal to 180. So this would be x, that's the first angle, plus 2x, that's the second angle, plus x plus 12, which is the third angle, has to equal 180. And the way you do this from an algebraic perspective, you add up all the x's. X plus 2x plus x is 4x, plus 12 equals 180. Then you'd subtract 12 from each side again. Hopefully you know how to do this from basic algebra. 180 minus 12 is 168. And so you get each side divided by 4. And x equals 168 divided by 4. Well, 160 divided by 4 is 40, so 168 divided by 4 is 42. So x is 42. Now, if we filled it back in over here, so this is 42. This is 2 times 42, which is 84. And this is 42 plus 12, which is 54. Of course, one way to check our answer to see do they actually add up to 180. And if you add them up, 42 plus 54 is 96. 96 plus 84 is 180, so it works. So the question is, what is the measure of the largest angle? And of course, the largest angle is 84. So that is our answer to that one. Again, there are a few things you needed to know for this one. You needed to know that essentially all the angles in a triangle have to add up to 180 degrees. Our last homework question, our last question for homework number 1 is a landscape designer is working on plans for a residential yard. Our client wants a privacy hedge to be planted on the sides of the rectangular backyard. The side bordering the house will not be planted. It gives you a diagram over here, so you don't have to memorize any of this stuff. The plant spans 5 feet when mature. If the backyard is 50 feet deep and 80 feet long, and there is no plant at the corners of the hedge, how many hedge plants will be required? Okay, well, let's figure this out. It should be fairly simple. Now, since each one is 5 feet, it is going to take 10 hedges on each side. Or on this side, it's going to take 10 hedges, 10 to cover this, and 10 hedges to cover that. Now, there is one at the corner over here, so we're going to put one over here and one over here. So how many across the top are you going to need? Assuming the hedges can count for the top also, these ones at the corner can count across the top also, because hedges grow in all directions like this. So instead of 80, normally you would need 16 of them. But because you already have 2 that count, and I guess these corner ones count double because they're right at the corner. So it looks like you'd need 14 of them left. So you got 10 and 10 and 14, which seems to me you would need 34 hedges altogether. Okay, so that's all for homework 1, and in the next section we will look at homework 2. Now we're going to go over homework number 2. So let's go ahead and do that. This is a little bit more conventional than homework number 1. This is all about angles and knowing the rules of angles, when they operate, how they operate, etc., etc. So let's take a look at number 1. I'm going to put it up over here on the big board over here, and I'm going to copy and paste the question, which should be right over here. Okay, there we go. So we've got a whole bunch of angles. FAB is 30. Now remember, FAB is, you look at the angle on the middle one in between the 2 line segments. So FAB is this one. So this is 30. Let me use a little bit of a thinner line so you could see. Fine, this is 30. GAD is 23 in there. And G and F are collinear, which means G and F are on a line. Fine, no problem. Okay, what is the measure of DAE? Sorry, I forgot one more, and that was, of course, CAB is 66. So this one is 66. Now, the first one we can fill in. I'll use a different color because these are the ones we're going to fill in now. Well, we know that GAF is a line, and we know that lines altogether have to equal 180 degrees. All lines, the total angles of a line have to be 180. So this one has to be 180 minus whatever is over here. 66 and 30 is 96, so 180 minus 96 is 84. So this we can fill in as 84 right away. What about DAE? Now, DAE, oh, one more thing I forgot, of course, and that is BA is perpendicular to EA. BA is perpendicular to EA. These 2 lines are perpendicular to each other. This and this. That means together they equal 90. Now, if together these 2 equal 90, so if this is 30, so this has to be 60. And we're going to slowly fill in all the rest of the angles. Now, of course, this side of the line over here also has to equal 180 altogether. So 180 minus 60 is 120, minus 23 is 97. So this one has to be 97 degrees. So we've put in all of the all of the angles over here. So now let's go ahead and answer these questions. DAE we put down as being 97. Name 3 pairs of supplementary angles. Supplementary angles are angles that equal up to 180. Pairs. So, well, what we know that everything on this line is 180. So how about if we use this angle, BAG, and BAF, that would have to equal 180, because really any two angles on the line. So let's take this big angle and this small angle. So let's say one of them is BAF, and the other being BAG. A second pair might be the opposite, this angle and this angle. In other words, CAF and CAG. Okay. And the other side we could use the same. You know, any two angles on this line from the opposite direction also. How about FAE and GAE? In other words, this angle and this angle. Okay, how about C? Name all the pairs of complementary angles. Complementary angles means angles that equal up to 90 degrees. Well, let's see. What angles are there? Let's see for C. Well, we know that these two have to equal up to 90. So let's try BAF and FAE, because 30 and 60 is 90. Are there any other pairs that equal up to 90? I don't really see any others that are going to equal up to 90. Okay. Name 2 adjacent angles. And adjacent angles means next to each other. There's almost an unlimited number of adjacent angles. DAE and EAF, BAF and EAF, CAB and CAG. Those are all adjacent angles to each other. Question number 2. In the figure, ABP is 72 degrees. ABP, 72, so let's put a 72 in here. And the measure of DPE, it's DPE, is 55. What's the measure of BPD? Okay, well, that should be simple enough. Notice you have these little perpendicular sign down here, which means CP is perpendicular to APE, which means that each side, in other words, this angle and this angle, have to be 90 degrees each. So if this is 55, this has to be 90 minus 55, which is 35. Sorry for that, for the sloppy writing. This side over here, of course, has to be 90 minus 72, because this whole thing is 90, this is 72, so this has to be 18. So they want to know they want to know BPD. So they want to know, like, the V over here, BPD. Well, BPD, well, you got 18 on one side and 35 on the other, so 18 and 35 is, of course, 53. It's just, all these things are just a matter of filling in the angles and just using the next logical progression. Question number 3 asks us a bunch of triangles over here. The lines mean they're equal to each other. Like AB is equal to BC over here. This means a right angle, of course. These means they're equal to each other. GH and I, all these sides are equal to each other. This means it's a right angle again. Okay, so which ones are scalene? Scalene means no sides are equal to each other. No two sides are equal to each other. So the scalene ones, I'll mark them. This would be a scalene one because it doesn't say any two sides are equal to each other. So I'll mark this with an S for scalene. This looks like a scalene, and this looks like a scalene. The others are either isosceles, when you have two equal to each other, or equilateral, which means that all three sides are equal to each other. Which ones are isosceles? Well, this one looks like isosceles because it's got two sides that are equal to each other, and this one looks like isosceles because it has two sides that are equal to each other. This one over here would be an equilateral triangle. That's actually question D. Which ones are right triangles, which means a triangle with a right angle? Well, this one looks like it has a right angle. That's this thing over there. And this one looks like it has a right angle. The others do not. Easy enough. Equilateral triangle is, of course, only this one, because all the sides are equal. And which ones are obtuse? Obtuse means it has an angle that's more than 90 degrees. Now, it looks like this one looks obtuse, because it's got an angle that's more than 90 degrees. This one looks like more than 90 degrees, and this one also looks like more than 90 degrees, so we'll label this one as an obtuse also. Just a matter of recognizing different types of triangles for this question. The next question is about a prism. A prism essentially is a triangle, but in 3 dimensions. Not a pyramid, but where you have two, like a tent, where you have a rectangle on the bottom. A, B, F, D is a rectangle, and then you have the sides going up. I mean, this kind of a shape is like a tent is a prism. Name the bases of the prism. Well, the bases are the sides that are the outside of the bottom of the prism. BF, FD, DA, and AB. These 4 bases. I'll put them in red over here. This would be the one. This would be one base. Actually, it's black. This would be a second base. This would be the third base, and this would be the fourth base. Again, it should be fairly obvious why. Lateral faces of the prism means not the base. So the base we just looked at, which would be A, B, F, D, this rectangle down here, the lateral faces would be the opposite. There's really 4 different triangles over here that would be the lateral faces. This area, A, B, C, this triangle, then this wouldn't be a triangle, this would be a rectangle, B, C, E, F, this whole side. Then the other ones that are hidden from view are the back, the opposite side. If this were solid, you wouldn't be able to see DEF as a base, and you wouldn't be able to say ADEC, this one in the back over here. This whole area over here would be hidden from view, and this one would be hidden from view. The ones that wouldn't be hidden from view, I'll put in green, would be this one over here, this rectangle, and this triangle over here. The edge are all the lines at the edge of the prism, and there's a whole bunch of them here. There's AB, there's BC, these are all the lines at the outer edge of the prism, AC, CE, DE, DF, essentially all the lines that are over here. Question 5 is actually a very easy one. Question 5 says a surveyor measured his angle to be 13 degrees, 15 minutes, 36 seconds. Now, the degree can be divided up into 60 minutes and a minute into 60 seconds. Nothing to do with time, but if you're measuring something smaller than a degree, you can divide up a degree into 15 minutes, and you can divide it up a minute into 60 seconds. Well, a degree into 60 minutes and a minute into 60 seconds of a degree. So 13 degrees, 15 minutes, and 36 seconds essentially means 13 degrees, and then 15 60th of a degree, and then 36 60th of a 60th. In order to use this measure in calculations, you have to turn it into degrees, express this angle in degrees as a decimal fraction of 1 degree. Well, since a minute is 60 seconds, so a 15 degrees is a quarter of, 15 minutes, this middle thing over here, is about a quarter of a degree. So it would be 0.25. It would be about 13.25 degrees. That would be 15 minutes. And so I think you can round it off to that. You can just, at the 36 seconds would add a little bit, but usually you can go to 2 decimal places. So in other words, it would be about 13.25 degrees, which is about 13 degrees and 13.25 degrees. You can write that in over here. If you were adding to more decimal places, then you might have to factor in this 36 over here as well. Question 7 requires us to do a little bit of artistry ourselves. Let's see, an airplane takes off from an airport bearing along AB of north 13 degrees east. So let's draw, in order to visualize this, let's draw a flat line, and this will represent the ground. This will represent straight. Okay. And let's put, just to make it nice and easy, let's put north up here. Let's put east over here. And let's put west over here and south down here. So this would be a straight east-west line. So this is of north 13 degrees east, which means let's start from a point in the middle over here, and let's draw over here to a point of 13 degrees. So let's put our 13 in here. Then a second plane leaves the airport at bearing north 30 degrees west, so on the opposite side. It doesn't matter if we draw it precisely, but let's try to draw it so that it looks somewhat normal. 30 degrees here. This is 30 degrees north of west. That's along AC, so we'll put a C over here. On this side, it's at along AB, so we'll put a B over here, and we'll put an A in the middle. A third plane leaves at south 87 degrees west, 87 degrees south of west. So now we'll take along AD. So let's do something like this. And we'll put the D over here. So we'll make this 87. So what do they want to know? They want to know the angle of the first and second planes. Third one doesn't really look like it's an issue. This one doesn't look as necessary, but the point is, since this is a flat line, these three angles, angle 1, angle 2, and angle 3, have to be supplementary, which means they have to equal 180 altogether. Now, if this is 30 and that's 13, so 180 minus 30 is 150. 150 minus 13 is 137. So this one has to be 137 degrees. And that seems to be the angle between the first and the third planes. Okay, homework number 3. And this is about really, different dimensions in geometry. The first question is about the perimeter. Perimeter is actually very easy. You just count up all the sides. The lengths of all the sides is the perimeter. So these are actually fairly easy. Let's take a look at this one. Well, these double ticks means that this side is equal to this side, and the single tick means that this side is equal to this side. So if this is 2, then this is 2, and if this is 8, then this is 8. So if you want to do the perimeter, just add up all the sides. 8 plus 8 is 16, plus 2 plus 2 is 20. So the perimeter of A is 20. Second one is just as easy. The single ticks means this is equal to this, so this is 3, so this is 3. This is 5.5, so this is also 5.5. 5.5 plus 5.5 is 11. 3 plus 3 is 6, so 11 plus 6 is 17. This one, how many sides we got here? 1, 2, 3, 4, 5, 6, 7. It's a septagon. There are 7 sides. And each side, the ticks mean they're all equal to each other. So it's an equilateral septagon, if you will. There's 7 sides, and each one is 2.4. So it's 2.4 times 7, which is 16.8, I believe. So that's your perimeter. 16.8. This side, none of them are equal to each other, so you just got to add them all up. Let's see, 2.1 or 1.95 plus 2.0, that makes 4. 6.1, 8.2, 9.8. Looks like 12.05. Again, you can do it in a calculator. I just did it in my head, but looks like the perimeter here is 12.05. Just added them all up. Fairly simple, fairly straightforward. Just perimeter, add them all up, see what See what they equal altogether. Okay, number 2. Let me drag that over here from the homework. There's only 4 questions on this particular homework. Some of them are fairly complex. Find the area of the shaded figure. Assume the curves are semicircles. Round the answer to the nearest hundredth. Okay, so really what you need in a shaded area question is you need to figure out the whole shape and then subtract whatever is not shaded. Now this is a rectangle, the entire shape, if you would include this side over here, which is not drawn, but if you would assume that there were a line that's drawn down here, that would be a rectangle, of course. So the entire rectangle, the area of a rectangle, is always the length times the height. So it would be 14.2 times 6.8. That's the entire amount, which according to my trusty calculator, and again, no reason not to do these on a calculator, is 96.56. So the entire thing is 96.56. That's the whole rectangle. Now you got to take out the semicircles. Now the good thing about this, the easy thing that this does, is that it gives you 2 semicircles, and 2 semicircles is 1 whole circle. So you can just take 1 whole circle, pretend you combine them. Now if you combine them, the way to figure out the area of a circle is that the area of a circle is pi times the radius squared. The radius is half of the diameter. Now this whole line over here is 6.8, so half of that, the radius of the circle, which would be from the middle to the end, would be 3.4. So the area of the circle would be pi times 3.4. Now we're going to use 3.14 as pi. We'll round it off because you only need to the nearest hundredth. So I'm going to do 3.14 times 3.4, which I'm doing on my calculator. I'm sorry, I forgot to square the 3.4. So first thing I got to do is I have to square the 3.4. So that's 3.4 times 3.4, which is 11.56. So A equals pi, which we're going to round to 3.14 times 11.56. So we're going to do that little multiplication on my little calculator over here, and we get 36.298, so we'll round it off to 36.30. And so this is the area of the circle, in other words, the whole circle, which is these 2 semicircles, this semicircle and this semicircle. So the area of the shaded region is 96.56 minus 36.30, which comes out to 60.26. This is the area of the shaded figure, or the shaded region. All we did, figured out the whole area and subtracted the light area. And again, if you're having trouble with any of these, please feel free to, to pause it, to rewatch it, or whatever it is. This is a video, of course, so you get to watch it as many times as you like. Okay, let's see number 3 over here. A sprinkler is set in the corner of a rectangular lawn 11 feet by 25 feet. So let's draw a rectangle that represents the lawn. A rectangle. Let's do the width over here. Whoops. So we'll draw this over here. And we'll make this the long way. So we'll make this over here, and then we'll draw this side and this side. All right, good enough. Anyway, so this is 10 by 25. It's a rectangle with 10 by 25, so we'll put a 10 here and a 25 here. If the maximum distance the sprinkler can reach is 10 feet, so the sprinkler is set in the corner. So the sprinkler will set right over here, And the maximum the sprinkler can reach is 10 feet. So the sprinkler, I guess, goes around. The sprinkler can go around in kind of a circle. So it can reach 10 feet up. It can reach all the way to this side, and it can reach about 10 feet over here. So the shape that it can reach is actually kind of a quarter circle. Let's draw a little bit of a better circle. Something like this. It doesn't really matter if it's even, but the point is this can only be 10 feet in this direction and 10 feet in that direction. So what are we talking about? What percent of the lawn will be watered from this position? Good question. So what are we looking for? We're looking for this area as a percentage of the entire area. It's an interesting question. Okay, now the previous question we had a semicircle. Here we've got about a quarter of a circle. So let's figure out if this would be a whole circle. If this would be a whole circle like this, what would the whole circle area be? And then we'll just divide it by 4. That should be enough. It should be simple enough. Because it's a quarter of a circle. You can envision this as being a whole circle, and only about a quarter of a circle, because it's put in the corner. It's kind of a silly thing to do. If you wanted to do the maximum, you'd put it in the middle, but that's not the question. The question is it's put in the corner. So this is a quarter of a circle. So again, the area of a circle is pi r squared. Now the radius here is 10, because if you did a whole circle, the radius is the distance to the end of the circle, which is 10. So it's 10, the area is pi times 10 squared, which is 100, of course. And pi will do as 3.14. 3.14 times 100 is 314. So we'll round this off to approximately 314. What is the area of the entire lawn? Well, obviously what I forgot to do is to divide this by 4. The area of the whole circle would be 314, but since this is only a quarter of a circle, we're going to divide this by 4. Now 314 divided by 4, well, let's see, 320 divided by 4 would be 80. So 316 would be, so it would be 78.5. And again, you can do this on a calculator, but it is fairly simple. I just did 320 divided by 4, which is 80, so take off 6, so it's 78.5. We're rounding it off to 78.5. And the entire area of a rectangle is the length times the height. So for the whole rectangle is the base times the height, or the length times the width, doesn't matter which way you call it. So that's 25 times 10, which is 250. So the percentage is 78.5 over 250. And I'm going to divide it on my calculator here, 78.5 divided by 250, and I'm getting, interestingly enough, 314. 0.314. And 0.314, to get the percentage, which they ask you, you just slide the decimal point over 2 slots. So your answer would be 31.4%. Ironic that we got the same number as we did in terms of pi. So it doesn't really look, let's just make sure that we did it right. Again, 10 by 25, which we did. The maximum of the sprinkler is 10 feet, so 10 feet in this direction and 10 feet in this direction, which is a quarter of a circle. Pi r squared is 100 times pi, which is divided by 4 is 78.5. 78.5 divided by 250, yeah, that looks about right. The drawing isn't great. The real semicircle would probably look more something like this, so it looks more like 30% when you do it this way. But anyway, that would be the answer, 31.4%. Question number 4 is an interesting one. These are interesting. These are fun. At least I think they're fun. Anyway, you might not agree, but that's okay. What's the surface area of the prism? Now, the prism means kind of like a box except a rectangle. This is a rectangular prism. That's okay. It says it's a rectangular prism, as a matter of fact. It says now the rectangular, of course, means the opposite sides are equal. So the 9.1 over here and 9.1 over here. This side would be 13.5. This side would be 9.1. These are actually squares on the outside. Now the surface area is the total amount on all surfaces. This area, the back area over here, the back area over here, the area on top, and the area on bottom would be all the combined surface areas. So if we had 6 surface areas, I'd label this as 1, this side over here. The bottom I'll label as 2. This side, in other words, this box over here, the one facing us, I'll label as 3. The back I'll label as 4. The top I'll label as 5. And the back area over here I'll label as 6. It doesn't really matter which one you do. So let's do the one facing us. Well, the one facing us is a square, 9.1 by 9.1. Now the square, you just multiply any side by itself. That's 9.1 times 9.1. So the first one I'm getting as 82.81. Now let's do 2, which is the bottom. Now the bottom one is 9.1 times 13.5, which I'm going to do on my calculator. 9.1 times 13.5, which is 122.85. Number 3, which was, what was 3? 3 was the one facing us, this rectangle, this one over here, the one outlined by this side, this side, this side, and this side, is also it is also 13.5 times 9.1, which of course is also going to be 122.85. Side 4 was the back wall, which is the same as the front wall, so that's also going to be 82.81. Side 5 was the top, this one, this, and this, which is the same as the bottom. So side 5 is going to be 122.85. Notice it's going to be easy because a lot of them are the same. And side 6 was the back wall as well, which is essentially the same thing. Also 122.85. Only 2 real dimensions here. The front wall and the back wall were the 9.1 by 9.1. The other 4 sides, on each side of the prism, and the top and the bottom, were 122.85. So I am going to do that calculation. These 4, if you multiply these 4, it becomes 491. You can just do it. It becomes 491.2, and 82.81 times 2 was 165.62. So if you add these up, again, without even using a calculator, this becomes a 7, that becomes a 5, and that becomes a 6. So altogether, you've got 657.02 square feet as the total surface area over here. Homework number 4. A lot of interesting application type questions. A baseball diamond is 90 feet on a side. This is actually true of a real baseball diamond. It's 90 feet from home to first, 90 feet from first to second, 90 feet from second to third, etc. A ball is hit to the shortstop who's halfway between second and third. How far must he throw the ball to put the runner out at first base? Let's draw a little line to represent how far he's going to throw the ball. He's going to start from halfway between second and third, and he's going to have to get to first. So we're going to have to figure out how long this line is. Writing it very often makes it a lot easier to to figure out what the length is, or what the dimensions are. So let's fill in what we know. Well, we know from first to second is 90 feet. Now we also know what this side is, because it says a ball's hit to the shortstop who's halfway between second and third, which means this is 45. Now we also know that the bases are right angles. Oh no, I'm sorry. Yeah, of course, they're right angles. All sides of a square are right angles to each other. So this is a right angle. Now, so once we have these, we can simply use the very famous Pythagorean Theorem. And Pythagorean Theorem says in any right triangle, a squared plus b squared equals c squared, where c is the hypotenuse. Hypotenuse means the longest side of a right angle. So in this case, we've got one side is 45, one side is 90, and this one, the one that we're looking for, is the hypotenuse, because it's the one opposite the right angle. So it would be 90 squared plus 45 squared equals c squared, whatever c squared is going to be. And, let's get a calculator over here. 90 squared, which is 90 times 90, which of course is going to be 1800. I'm sorry, 8100, sorry. Plus 45 squared. Plus 45. Well, I'll start the other way. 45 squared is 45 times 45 is 2025 plus the 8100. So that gives us 10,125. So I'm going to write that over here. 10,125 equals c squared. Now, like any other equation, you can take the square root of each side in order to get c by itself. So c, which is the third side, equals the square root of 10,125. Let's get our calculator back up here. And we had this up over here, so let's figure out the square root. And the square root is 100.62. So it's approximately 100.62 feet. It goes on for more, but that's you can round it off to that. So it's a little bit over 100 feet, or 100.62 feet, to throw the ball from the shortstop hole to first base. Question 2, another interesting one here. We've got two trucks. One heads south at 58 miles an hour, and the other heads east at 63 miles an hour. After an hour and 35 minutes, how far apart are the trucks? Well, let's figure this out. First, we're going to do south. Now, south at 63 miles per hour, 1 hour and 35 minutes. Now, 1 hour and 35 minutes is, we need to figure out what percentage of that is, what percentage of an hour is that. Now, 35 minutes is what percentage of an hour? 35 divided by 60 is the same as 7/12. So it would be 7 divided by 12. So essentially 0.58. So it's, in other words, 1 hour and 35 minutes is 1.58 hours. That's the first thing we needed to know. The amount of time over here is let me write that. 1.58 hours. Now, so how far did this go down? Well, he went south at an average of 58 miles an hour for 1.58 hours. So let's get our calculator up here. And our calculator is 1.58 times 58. So that's 91.64. Okay. 91.64. East, how far did he go? Well, he went 63 miles an hour, also for an hour, for 1.58 hours. So, let's do that again over here. What's 63 miles per hour? Okay. So 1.58 hours times 63 miles an hour is 99.54. All right. 99.54. Okay. So we've got a right triangle because one went due south and the other went due east. So this is certainly a right angle. Whoops. Oh. This is a right angle. So you can use the Pythagorean Theorem again. This is 99.54 squared plus 91.64 squared equals c squared. And for that, honestly, I'm just going to use Excel rather than I can do it on the calculator, but just the way you would do it on a calculator, multiply this by itself and put that number here, multiply that number and by itself and do that number here, and then take the square root. So I'm going to just do it on Excel, and the way I'm going to do it on Excel is I'm going to say equals square root of 91.64 to the second power. You can use this little caret to the second power plus 99.54 to the second power. And it looks like about 135.3 is going to be, which makes sense. So that's about right. So if you did that, if you multiplied, if you took this and squared it, and took that and squared it, added them together, take the square root of the product, you're going to get approximately 135.3. Okay. About 145.3 miles. The next question is, again, a Pythagorean Theorem question. 12-foot ladder will be used to paint the exterior of a house. Now, the foot of the ladder needs to be 3.7 feet from the base of the house. Let's draw the house over here. You know, the side of the house goes straight up and down, so we'll draw this as a straight line. Okay. The ladder is going to be 3.7 feet away from the base of the house, but it's going to reach up 12 feet. It's going to reach it's going to be a 12-foot ladder. So let's put that over there, and then let's use that distance. Well, from the house. So what do we know? We know the ladder is 12 feet. So we're going to make this a 12. We know that it's 3.7 feet away from the house. And what are we looking for? We're looking for the maximum height of the ladder, so we're looking for x. Now here, unlike the previous two examples, we're still going to use the Pythagorean Theorem, but remember this here is the one that's the right angle. So this is going to be the c. So we can do a squared plus b squared equals c squared. The a can be 3.7 squared, plus b, we don't know what that is, so we'll call it x squared equals 12 squared. Well, again, 3.7 times 3.7 is 13.69. 69 plus x squared equals 12 squared, which is 144. And if you're doing this, you just subtract 13.69 in order to isolate x, minus 13.69, which is going to get you x squared equals 130.31. So we've got 130.31, and take the square root of that. So let's bring up our calculator here. Where's our calculator? Here's our calculator, which is still stuck on, whoops, help. Okay, which is still stuck on previous example. Okay, we've got 130.31, and we'll take the square root, which is 11.42. So it's going to reach approximately, this is an approximate number, but it's going to reach approximately 11.42 feet up the house. 12-foot ladder, base 3.7 feet away, is going to reach about 11.42 feet up the house. Okay, here's another interesting one. A board foot is the volume of a piece of wood 1 foot by 1 foot by 1 inch. Deck is designed as below. 1 inch by 6 inch boards are used for the surface of the deck. How many board feet are required for this part of the job? Well, okay, first let's figure out the surface area. It's 1 foot by 1 foot. So what's the surface area of this entire thing over here? Let's get this diagram over here and make it a little bit bigger so that we can, draw on it and make it make a little bit more sense. All right. There we go. Okay. So let's separate this out into two different sections just to make it two nice and easy shapes over here. Let's put a little border over here, and just a little easier to visualize that way. And let's add them together to see how much there is. Well, the big shape, the big one, is 20 by 8. Now the area, we know an area of a rectangle is the width times the length, or the base times the height. 8 times 20, which is 160. Okay, that's going to cover this whole area. Whoops. And then we've got the little area over here, which is 3 by 3, which is 9. So the whole thing is 169. That's the surface area. But that doesn't cover the whole thing. It says a board foot is 1 foot by 1 foot by 1 inch, and the deck needs to be 1 inch by 6 inch boards for the surface. So we need 6 times this many, really, because these are only 1 inch deep and we need 6 inches deep. So we need to multiply this number by 6, and 9 times 6 is 54, and we've got 1, 4, 10. So according to my calculations, we've got 1,014 board feet are necessary to cover the deck. Again, I just kind of used the surface area first, broke it apart into manageable pieces, and then once we did that, we realized these are only 1 inch thick, and we need 6 inches thick, so just simply multiply by 6. Another practical application. We've got a cardboard box that needs to be 3 feet long, 1.5 feet wide, and 2 feet deep, and allowing 5% for waste. How much cardboard will be required to build this box? Well, a box is a rectangular prism. Now, the way to figure out the volume of that is simply to multiply all the dimensions. Multiply the length times the width times the height. So we've got 3 times 1.5 times 2. Now, 3 times 1.5 is 4.5. 4.5 times 2 is 9. And then we need 5% of 9. Now, 5% of 9 should be relatively easy, but just to make sure, let's do it on the calculator. Whoops, again, I think I did this last time too. Okay, 5% is 0.05 times 9 is 0.45. So we need to add a 0.45 cardboard. So basically it's 9.45 cubic feet is the total amount of cardboard we're going to need. 3 times 1.5 times 2, and then an additional 5% to cover wastage. Okay, our next question, we got another practical question over here. This is a ramp. A ramp is designed as below. The surface is to be made of 1 inch plywood. Then the top surface is to be covered with non-slip coating. Let's make a nice big one so we can see it a little bit better. In fact, let's then delete this one so it doesn't confuse us. Okay, so let's see. We've got, these are all feet. Okay, good. The surface is to be made of 1 inch plywood. So how much plywood is needed and what area will be covered by non-slip coating? Now the top surface, I guess the top surface will be just this here. And all the rest of the stuff is covered by plywood. So let's start with coating. The top surface is just this one over here. So just the coating is the easy one. Coating is just the top surface. The top surface is just the surface area of this one up here. How long is this one? Well, this one is 4 because this down here, this area and this length and this length are the same. And this is 1.5. So the surface area of this rectangle is 4 times 1.5, which is 6. So that's 6 square inches of plywood. Now, I'm sorry, of coating. Now we need the plywood. Now the plywood is all the other sections. How many sections are there? Where there's the ramp itself, then there's this side of the ramp, that side of the ramp, the bottom of the ramp, and the outside of the ramp. So there's 1, 2, 3 in the back, 4, 5. So it looks like 5 of them. Okay. Let's start with the easy ones. Let's start with the bottom, which is the bottom one over here. Well, the bottom over there is 12 times 4. So the bottom, so that's the first one. 12 times 4 is 48. Okay. Now let's try the back. The back is 4 by 2, it looks like. Again, because it's this one, which is the same as this. So it's 4 times 2. Whoops. Is 8. Now, we've got the inside and the outside, which are going to be the same. In other words, it's going to be 2 of the same. This trapezoid and this trapezoid are going to be the same. There's going to be 2 of them. Now with a trapezoid, you got to figure out the average base times the height. So for the trapezoid, what's the average base? Well, it looks like the top base is 1.5 and the bottom base is 12. So the average between 12 and 1.5 would be, I guess, 6.75, I imagine. Yeah, 12 plus 1.5 is 13.5, 6.75, right, okay. So the average base is 6.75, and the height is 2 of both ones, so 6.75 times 2, which is 13.5, and there's 2 of them, this side and that side. 0.5, and we've got one more, and that's the ramp itself. The ramp itself is this area. The ramp itself is an interesting one. The ramp itself, we've got to figure out. Let me erase all this stuff and get a new diagram here, and make this a little bigger, because this is going to be a little more complicated. So to figure out the ramp, we need this line multiplied by this line. Well, the bottom one, of course, is easy. That's 4. We need to figure out what this is. Now, this is actually a diagonal, so I guess we can use the Pythagorean Theorem to figure that out. This is an interesting one. I'm going to draw a line down here, and let's see if we can use that. Yeah, this makes sense, actually. This is a hard one. This height, of course, would be 2, because it's the same as this. This length would be the entire minus the 1.5. It's the 12, which is the whole bottom, minus the 1.5, which was this area. So this one would be actually 9.5. Now we can use the Pythagorean theorem to figure out what this diagonal would be. The diagonal would be, let's say, 2 squared plus 9.5 squared equals c squared. And I'm going to take out the calculator here. Okay, 9.5 squared is 90.25, plus 2 squared, which is 4, equals 94.25. Let's take the square root of that to plug it into the Pythagorean theorem, and we've got 9.71. So we're going to estimate this thing as 9.71. And of course, this side is the same, also 9.71. So this whole area over here would be the width, which is 4, times 9.71. So we've still got the 9.71 on the calculator, so while we're here, let's just multiply it by 4. We've got 38.83 equals 38.83. Now, if we add all these up, we should get the total amount of plywood necessary. We got 48 plus 8 is 56. 13.5 times 2 is 27. So 56 plus 27 is 83. And then 83 plus 38.83 is 121.83. Again, I guess the process is the important thing over here. It was a pretty hard question, but I guess if you just draw, you can draw as many of these imaginary lines as you like in order to figure out the ultimate answer. Homework number 5, which continues with angles, measurements of angles, and, well, stuff like that. This is question number 1 for homework number 5, and that is in the figure shown below. AC is congruent, which means equal in this context, to BE. So let's mark this with a tick, and BE with a, AC is CE, which is this whole thing, basically this whole line over here, okay. And BD is congruent to BE. BD is congruent to BE. Okay, so these two are isosceles triangles. This little triangle over here and the big triangle AEC. And AE is congruent to DE. AE, actually let's use double ticks for this. And AE is congruent to DE. So we'll use triple ticks for this. So we've got a lot of congruent triangles here. Okay. AED is 105. So where's AED? AED. So this whole angle over here is 105 degrees. Find the measures of AEC. AEC, that's this one over here. We'll call that angle 1 because that's the one we're looking for. And CAB. CAB is angle number 2. Okay, and here I've taken the liberty of making the figure a little bit bigger. Now, the key thing, of course, with this sort of thing is that when you have an isosceles triangle, the bases are equal. So before we even figure out any of these things, I'm going to see what we can do to figure out what some of the other measurements are. Because what I always do with these things is just try to look at what can you fill in, and then hopefully it'll eventually fill in what you need. All right, now this is 105 degrees. So that means this big triangle, AED, of course, all triangles have to equal 180 altogether. Now, this angle over here, EAB, and this angle over here, BDE, have to be equal because those are the bases of an isosceles triangle. This big triangle, ADE, is isosceles, and since this is equal to this, these two base angles have to be equal. And this one up here was 105, which means there's only 75 degrees left between the two bases. And so each one of them is going to be half of 75, and half of 75 is, of course, 37.5. So I'm going to write 37.5, and so I'm going to put those over here, a 37.5 here and a 37.5 there for this whole big triangle. Okay, now is there anything else that we can figure out? Well, the thing that strikes me right away is, what about this triangle, BED? We know that BE is equal to BD. So that means these two base angles, this one and this one, have to be equal. So I'm going to take that 37.5 and put another one right over here. Okay, see, this is helpful because that's the base two angles of this triangle over here. Now, we know that this whole thing, this whole angle 1, is 105 total. So we know at this whole angle, AED is 105 because we were told that, and this part of it is 37.5, which means the other part, BEA, or CEA, or AEC, which happens to be one of the ones that we're looking for, has to be 105 minus 37.5. Now 105 minus 37.5, so that has to be, angle 1 has to be 67.5. because that's 105 minus 37, so I'm just going to put in 67.5, and we'll move this over here. So that's part of our answer. So already we got 67.5 for this one. Now, if just out of curiosity, I mean, again, we could probably figure out number 2, but in order to do that, we can keep filling out the other angles. Well, we can figure out this one because together they have to equal 180. This is 37.5 and 67.5, so combined that's 105. So what's left over here is 75, of course. So I'm going to put a 75 here. And we will put this over here. Now this, of course, has to be 105 for two different reasons. This has to be 105 because this triangle has to be 180 altogether, and already 75 is used up by this 37.5 and this 37.5, so there's only 75 left. And also because it's a linear pair, it's a supplementary angle with this one. And a linear pair, supplementary angles have to equal 180 altogether. So this has to be 105 regardless. So I'm going to put 105 in here, and okay, I'm going to put it over here. And also, that means that this has to be 105, again for two different reasons. First of all, because it's a vertical pair with this one. Remember, when two lines crisscross, the angles that they make that are opposite each other have to be the same. Plus, it's a linear pair. It's supplementary angles with this line, CBE. So it has to be supplementary with this one. This one is 75, so that has to be 105 to equal up to 180. Okay, now let's see if we can figure out. We need to figure out what this one is. How can we figure that out? Okay, well, that shouldn't be too hard. We know that this is equal to this, which means that this angle, which is the base of the big triangle AEC, has to equal to this. And this, the total is 67.5. This is 37.5, so whatever's left over here has to equal up to 67.5, so it looks like angle 2 has to equal 30 in order to equal up to total of 67.5. I'm going to put that in, and that's our answer. So we could then if we wanted to figure out this one, just out of curiosity, well, this is 165. I'm sorry, this is not 60. This is 30. That's my mistake. It has to be equal 67.5 altogether, which means there are 30 left. So let's put the 30 in here, and that's our answer. This CAB is 30, AEC is 67.5. So those are our answers. And if we wanted this angle, which is the last angle that we haven't done yet, well, that should be easy enough. There are many different ways we could figure out this. We could figure it out from the big triangle ACE. This is 67.5. This is 67.5. Combined, that is 135. And so there's only 45 degrees left for this angle, so this would have to be 45. The other way we could figure it out is by this triangle, ABC, which this is 105, that's 30, that's 145, which means 135, which means that there's 45 left. So either way, angle C would be 45. Question didn't ask us for it, but for the sake of completeness, let's put this in. The one thing you'll notice is that once you get a few on these kinds of problems, once you get a couple of them, the rest of them will not only be easy, but there'll be multiple different ways that you can figure out the angles of many of the others. So now we've pretty much gotten all of the angles in these triangles, even though we weren't asked to. Question number 2 is a similar one. Following figure GBC is 36. So where's the 36 that we're going to put in here? All right, where's the 36? Let's capture this. GBC, we're GBC. So right over there, that guy over here is 36. And what do they want? They want GFB. Let's mark these with numbers. GFB, that's angle 1. Then BCE, BCE, angle 2, that's the big one here, BCE. That's this whole angle. Call this angle 1. And then CED. So this is angle 3. All right. Well, let's figure this out. We've got, let's see, we've got some right triangles over here, which means this is 90 degrees and this is 90 degrees. And this is an isosceles triangle, FCE. Here is another right triangle. Here's another right triangle. There are all sorts of goodies over here that we get. So what can we figure out based on what this being a 36? Well, the first thing I see is that we can work with this triangle, FBC. In other words, this triangle in the middle over here. And that is, this is isosceles. And because it's isosceles, the bases are equal. So this angle has to equal this angle. I'll make that a different color. And that should be easy enough to figure out. Now, an altitude, which is a right angle, goes to a line, bisects the top in a right triangle. So in other words, an altitude, and sorry, in an isosceles triangle. In an isosceles triangle like FBC, an altitude that goes straight up to the top and is a right angle on the bottom bisects this, which means this 36 is going to apply to the other side also. Let's put another 36 up here, which is common sense. If this is going to be directly to the bottom and these two sides are equal, so this has to split it up. So this 36 and 36 is 72. Now, this triangle has to have 180 altogether, And 72 is taken up by this angle up here, FBC, which means that the bottom two each have to split up that 108 left over, which is 54. So I'm going to put a 54 in two places. I'm going to put a 54 over here, and I am going to put a 54 over here. So far we've gotten one of our answers. We've gotten GFB, which is this angle over here. That's 54. So we've answered A. Now let's see what else we can do with this. Well, interestingly, look at this shape. ECFB. That's a rhombus, because this kind of kite. If you notice over here, this here, 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 this whole shape over here, I'll delete it as soon as I mark it up. But this whole thing over here, this kite-like structure, that is a rhombus. And in a rhombus, opposite angles are equal. In fact, in any parallelogram, opposite angles are equal. So this 72 means that that also has to be 72. So let's put a 72 over here. Let's get a little 72 and put a 72 over here. This has to be 72. Now, if this has to be 72, then these bases have the same rules, essentially. These bases also have to be the 54s, for the same reason that these had to be 54s. These had to be 54s because this was 72, and it was 180 minus 72 is 108, and 108 divided by 2 is 54. I have to split them up among here. And so this one has to be 54. Again, let's get two of these. One for here and one for here. Okay, good. So now we can get angle 2. You know, angle 2 is this big one over here. You got 54 over here and 54 over here. So the whole angle 2 has got to be 108, right? 54 plus 54. So let's put 108, and we can get that as our answer for BCE. BCE is 108. So now we've only got one left, and that's all the way down here. Okay, well, how do we figure it out? That should be fairly simple. We can use the fact that this angle here can be figured out because this was 108. This whole angle over here was 108. And this one is part of an ordered pair, is on a line with this. BCD is a line. And this angle, BCE, is 108. So that leaves 72 for this angle right here. Let's put a 72. Let's put that over here, and a 72. And based on that, we know what angle 3 is, because like all triangles, CED has to be 180 altogether. This is a right angle, so it's 90. This is 72. So that makes 90 plus 72 is 162, which means that angle 3, there's only 18 degrees left for angle 3. So we're going to put an angle, so 18 degrees is over here, and which means we can answer this by putting this up here. This one over here, angle 1, was the 54. So those are our answers. Again, the problem like this looks pretty intimidating when you look at it at first, because there are a lot of angles, and you know, sometimes you make the mistake of thinking you got to have a strategy. You know, you got to figure out like how are we going to do it. The truth is, you don't need a strategy. All you need to do is just put down what you have and just figure out what you can figure out. As long as you figure, don't even worry about the one that you have to get. As you get them, they'll all come into place. As you get them one after another, you just keep filling in, filling in, filling in. Eventually, you'll figure out the one that you need. You know, ABF, of course, is going to be the same. It's going to have all the same rules. This angle would be 72. This angle would be 90. This angle would be 18. And this whole big shape would work. There are many other ways, by the way, you could figure this out as well. The entire shape ABDE would be a rectangle, which means if this is 90, that's 90, that's 90, that's 90. 36 and 36 is 72, which leaves 18 over here. over here. That also leaves 18. Many different reasons why this has to, why these angles are gonna work. The next one is a proof. A proof you do by a statements and reasons column. In fact, I'm going to open up a Word file over here in order to do the proof. All right, I'm going to open it over here, and what I'm going to do is I'm going to put in a column. I'm sorry, a table, and I'm going to put in a statements column and a reasons column. So you know what? Let's put it on our Word file here. Just we got our diagram over here. We'll go back and forth over here. AC is congruent to BC. That's the big line over here. Whoops. Okay, AC is congruent to BC. These two lines are equal to each other. AF is congruent to BF. Prove that triangle EBC, EBC, this one here, is congruent to DAC, DAC. In other words, this triangle is congruent to this triangle. Now remember, in order to get a to prove two triangles congruent, you can do it by proving all three sides are equal to all three sides. SSS is congruent to SSS, all three sides together. You can do two angles on a side, or you can do two sides and the angle in between them. That's, of course, part of the fundamental idea, but that's really your three opportunities. Two angles on a side are equal to the other triangles, two angles on a side, all three sides equal to all three sides, or SAS, side angle side, consecutively, are equal to the other triangles, side angle side. Now, in these two triangles, you really kind of start off with two of them here. What do you start off with? Remember, we're talking about this triangle here, and this triangle here. These two triangles. Now, you really start off with two things because they gave you one of the sides. They gave you AC and BC. They gave you that right away. Now, they have a common angle, which is angle C. Angle C is an angle in both of them, so obviously an angle is equal to itself. So the only thing we need left is one angle or one side. Now, it seems to me we can do that relatively easily by getting this angle and this angle. If we do that, if we get this angle, well, now we've got angle, side, angle. We've got this angle is equal to itself, this side's equal to this side, and this angle is equal to this angle. How can we get this angle and this angle? Well, because of these two sides are equal, the whole angle A has to be equal to the whole angle B, because base angles of isosceles triangles are equal to each other. Then the little angles here and here, FAB and FBA are equal. And so therefore, what's remaining has to be equal as well. So how would I prove that from a perspective of putting that into statements and reasons? Okay, I'm going to put this over here while we work on it here. So let's look at it. So our first statement, you should really say that, say the givens also. So we'll say AC is equal to BC, segment AC, and because it's given. Okay, that's easy enough. Number two, we've got AF is equal to is congruent to BF. Is equal to BF, again, given. Now, we've got two different triangles again. We're looking for this triangle, and we're looking for this triangle. So we've got one angle that's common, and that's angle C. So I'm going to say angle C. I'm going to use this symbol for angle. Angle C is equal to angle C. Well, because angles are equal to themselves. That's simple enough. Okay, so now we've got one. Now we need two of the sides of the big triangles of EBC and ADAC, which is this, and we've got them. We've got side AC. Well, we don't even have to write again AC is equal to BC because we already wrote it. It's already given. So that's 2. Now let's look at the base angles. So let's try angle CAB. Angle CAB is equal to... You can, by the way, if you want to give them numbers, you can give them numbers and do it that way. It's a little easier, but I'll use the full angle names. Is equal to ABC, to angle ABC, because base angles of isosceles triangles are equal, and these are obviously base angles. Now, we're also going to do these two little angles, the green one. We'll say angle, let's just copy and paste this and change the letters to make it a little bit easier. FAB, call it FAB, is equal to ABF, or okay, again, because this is an isosceles triangle, AFB, so we'll do the same. Base angles of isosceles triangles are equal. Then we'll get to the next thing over here, to the orange ones. We'll say CAD. Whoops. Okay, CAD this time. This one is equal to EBC, which is this one, in other words, the orange angles. And I'm not even sure how to describe this, honestly. You know, I don't know if this is an actual theorem or a postulate, so I'm just going to write it in plain English. I'm going to say, since the big angles and the big angles were equal to each other, and the green angles were equal to each other, FAB is equal to that, the remaining parts of the two angles must be equal to each other. Again, there's probably some sort of a theorem or postulate there, but just to me it just seems like common sense. It seems fairly obvious that if the whole angle is equal and this whole angle is equal and the greens are equal to each other, then whatever's left over of the oranges has to be equal to each other. Well, now we've got an angle of this and a side and an angle. So then I'm going to say triangle, and I don't have a triangle symbol here, so I'm just going to actually type out triangle. EBC, and I should really use the congruent sign over here, but I don't have the congruent sign over here, so I'm just going to use the equal sign over here. If you're writing it out, you should use the congruent sign with the little squiggly thing on top of the equal sign. DAC, and for this one I'm going to say ASA is congruent to ASA. Angle side angle is congruent to angle side angle, which it is. Angle side angle to angle side angle. So these two are congruent to each other. Okay, number 6, another proof. In fact, the last 3 of these, or I'm sorry, number 5. Well, this is actually number 6. So I copied and pasted out of order. We can do that. That's no problem. We'll do number 6, and then number 5, and then number 7. AB is perpendicular to BC. Okay, that means this makes a right angle. DC is perpendicular to BC. This makes a right angle. Okay, simple enough. And AB is congruent to CD. So this equals that. Prove that angle BAC, this one over here, I'll make the one that we have to prove green, to this one, CBD. Okay? So let's figure out how we're going to do this. Now, in order to do that, the simplest way that I can see would be to get two of these triangles to be congruent to each other and then use corresponding parts. Corresponding parts is after you establish that triangles are congruent to each other, then everything in the triangles, all the angles and sides, have to be equal to each other. The corresponding parts of each ones have to be equal to each other. So let us take a look at this. So how are we going to do that? We've got two sides to either the little triangles or the big triangles like ACB and DBC. We can use the big triangles or the little triangles. Let's see which one we have. Well, I can see right away that we've got the big triangles very, very easily. In other words, BCD, this triangle, and ACB looks like we have very, very easily over here, because they're already giving us one of the angles and one of the sides. They gave us this side to this side and this angle to this angle, and this one, this side, BC, is common to both of them. This side over here is congruent to itself, and that's going to give us the two big triangles. And once you get the two big triangles, just use corresponding parts. That's simple enough. So it seems to me that this is actually a very easy proof. So let's see how to go about putting it together in plain English. Now this is the one we were using last time. So I'm going to take out all the videos. Take out all the statements. So in this one we had AB is perpendicular. You usually use the perpendicular symbol, but again, it's probably somewhere over here. Okay, I can't find the symbol, although I'm sure it's somewhere. Anyway, AB is perpendicular to BC because it's given. And also we had, what else? DC and BC. Yeah, same thing. DC and BC. And we were given AB is equal to CD, and that was also given. Okay. Whoops. Fine. Okay, so then we proved very simply that ABC and DCB are right angles. We'll say that. Angle ABC and angle BCD, this one and this one, are right angles because perpendicular lines form or meet at right angles. Again, there may be a more precise scientific mathematical way of putting that, but that's fine. Right angles, not tight angles. And then we will say that these two are equal to each other, which may be fairly obvious, but we should say it. We should say that these two angles equal to each other because perpendicular angles are equal to each other. They're all 90 degrees. Again, fairly obvious, but in proofs you want to make things as clear as possible. And then, so we've got a side, we've got an angle, now we get the last side. BC is equal to BC because line segments, you can call them sides if you want, are equal to themselves. Fairly obvious. Then we've got the two triangles. Then we've got triangle ABC is congruent. Again, I'm just using the equal symbol, but you should really use the congruent symbol. Is congruent to triangle BCD because side angle side. So we'll say SAS is congruent to SAS. Side angle side is congruent to side angle side. And then finally, the thing that we're trying to prove, that BAC is equal to, I'll copy and paste this to make it a little easier. BAC, which is the thing we're trying to prove, is equal to CBD, and the reason is because corresponding parts of congruent triangles are equal. Notice if this triangle is congruent to this triangle, so their corresponding parts, which clearly this angle and this angle do correspond to each other in the triangle, are equal to each other. So there we go. And then we've proven our case. Congratulations. Okay, so that is question number 6. Now let's go to question number 5, which we skipped, but now we'll do it. And there it is. Let's make it a little smaller so we can see it. In this figure, ACDF is a parallelogram. ACDF is a parallelogram, and AD and BE bisect each other. Okay, and we need to prove over here that BC is equal to FE. All right, I'm going to make this a little bit bigger. All right. So BC is congruent to FE is what we're looking for. BC and FE, these two over here. Just looking at it offhand, it looks to me like corresponding parts of this triangle, AFE and BCD, is going to be our best bet, but let's see what we're given. Okay, we're given this is a parallelogram. Now, parallelogram, first of all, that means that opposite sides are equal, so this is equal to this. It also means that the whole bottom is equal to the whole top. This all across. Maybe I'll indicate it like this. Okay. And we're also given that AD and BE bisect each other. Each one is half. So for example, this, I'll use one red tick. This is equal to this, and for two red ticks, this is equal to this because they bisect each other. They split each other in half. All right, prove that BC is congruent to FE. These two parts over here. Okay. Now, in a parallelogram, opposite angles are equal as well. So we know that this is going to be equal to this. Okay. So we've already got a side and an angle. We've already got this side, and again this side, and this angle and this angle. Now, the third side, let's see how we would get that. I mean, honestly, I'm just thinking of how we could get that. I see an easy way to get this side and this side, AE and BD, because these two triangles, this triangle and this triangle, we can prove congruent right away based on side angle side, because this and this are the two sides, and this angle, of course, has to be equal to this angle because they're vertical angles. They're a vertical pair of angles. So I can see that these two triangles are going to be congruent to each other right away, which would allow us to get this side and this side. But that wouldn't end the inquiry. That wouldn't give us the final tally, because then you just have side-side angle, and side-side angle is not good enough if the angle isn't between the two sides that you're working on. A different tact might be, and I'll use a different color, I'm just thinking out loud over here. A different tact might be, now opposite sides of a parallelogram are also parallel to each other. We can use this and this as being parallel to each other. And then, so therefore we can say that this angle equals this angle as alternate interior angles. Now, based on the alternate, because this is, it's bisected by one transversal. AD is a transversal that bisects, that intersects the two parallel lines, AF and CD. So once we do that, then we can show that this angle, EAG, is equal to that angle, ADB, because of corresponding parts of this middle triangle over these middle triangles over here. And then we can get these two angles. It's probably a little convoluted. We can get these two angles, the blue ones, because of because the two big angles are equal, so the smaller parts, like we did in the last one, and then we can get then we can get these triangles based on an ASA, angle side angle, or SAS, angle side angle side, and then we can get these based on corresponding parts. Now, there's probably a better way. I'm thinking of I'm probably there's probably a much simpler way that I'm just missing. Maybe if you're looking at it for a little while, you can figure it out. You can figure out what what I'm doing wrong, but I'm gonna try to. I'm gonna do it the long way here. Why not? So let's start our proof over again. This is gonna be a little bit longer than the other one, but that's okay. We have time. I guess I have time anyway. I don't know about you. All right, but this should be instructive one way or the other. So ABC. So what do we have? We've got ACDF is a parallelogram, because given, okay, and AD and BE bisect each other, also given. So what's our next step? Now what we did next is we got the interior. Okay, so we got the interior angles. We got the interior triangles, excuse me. I'll say EG and BG. EG equals BG because AD bisects AD bisects BE. In other words, this bisects this, leaving two equal segments. Again, it's not very mathematically precise, but it will do. Then we'll do the same with B. Then we'll do the same with AG and AD and GD. AG equals GD, and we'll use the same reasoning, except this time we'll say that BE bisects AD, leaving two equal segments. Fine. So now we've got the middle. Then we've got these two angles. We'll say angle AGE. Angle AGE equals angle BGD, because pairs of vertical angles are equal to each other, which means this, if you crisscross two diagonals, crisscross two segments, the angles opposite of each other will inherently be equal to each other. They're called vertical angles. Okay, now we've got the two triangles. Now we've got triangle, and this is AGE is congruent. I'll use equal, but again it should be congruent to triangle BGD because of SAS. This side, and this angle and this side. So we got SAS is congruent to SAS. Fine. Now we wanted to use what? Now we wanted to use AE and BD because of corresponding parts. So I'll do AE is equal to BD, this one and this one, and we'll do corresponding parts. I'll just leave it as corresponding parts. You should really write corresponding parts of congruent triangles are congruent, but it's fine for now. Okay, so now we've got those two. Now, what other angle are we going to want to use? Now, C and F we don't even really need, because we're going to use this angle and this angle. So we don't even really need angle C and angle F, so I'm not even going to bother to mention that. I am going to say these two sides, AF is equal to CD, and I'll just say AF is equal to CD, and the reason is because opposite sides of parallelograms are equal. Now we're going to work on this angle here. So I'm going to say the two big angles, FAD, angle FAD is equal to angle ADC, because they're alternate interior angles. So I'll say something like when two parallel. Actually, I should first say that these are parallel lines. that AF is parallel. We're going to use this next, so I'm just going to put this over here. So I'm going to say AF is parallel to CD because opposite sides of a parallelogram are also parallel. That's why it's called a parallelogram. So I'm going to say parallel. Then I'm going to say FAD, this angle here, the big one, is equal to this big one over here, ADC, because when two parallel lines are cut by a transversal, which just means a line that cuts through both, alternate interior angles are equal. Okay, these are alternate interiors. This and this are alternate interiors. Now we've got this one over here, the one with the three lines, this three greens and that three greens, EAG to GEB. EAG is equal to angle GEB. This we've got based on corresponding parts of the middle of these two triangles, the ones that we already proved. So for this, I'm just going to say corresponding parts. Okay. Now, this is similar to what we did last time. We're going to do these two angles. We'll do FEA. Okay, I'll just copy and paste this. This is FEA and BDG. Okay, because I'll say since the big angles, FAD was equal to that, and the smaller angles, these ones over here, whoops, which were EAG is equal to GEB, the remaining parts of equal angles must be equal. This is similar to the one we did last time. Now we've got this angle, and this side, and this side. So now we can get the outer triangles, the ones that have little blue squiggles in them. And so we'll say triangle AFE is equal to triangle BCD. And we will do that because of SAS, side, angle, side. So we'll say SAS is congruent to SAS. And finally, we've got the thing that we finally want, which was BC and FE. BC equals FE, and we've got that based on corresponding parts. So we'll just write corresponding parts of congruent triangles are equal. I bet there was an easier way to do this. Just thinking about it, but let's see, was there a better way? Yeah, there was actually a much easier way. Now that I think about it, I'm just looking at it. The easiest way to do this would be, instead of getting these two triangles, we could have gotten these two triangles, AGB and BGD. We could have gotten them on the same rules as we did before. We could have gotten them on side angle side, because we got this and this and this and this. Those are two sides of these interior triangles over here. Then this angle over here where the G is, and then the opposite angle, of course, are verticals. So we can get these two triangles, EDG and AGB, on SAS, that they're equal to each other. Then we can get the smaller segments, AB and ED, on corresponding parts. And AC and FD, the big ones, are equal to each other because they're opposite sides of a parallelogram. And then we can get BC and FE based on the remaining parts of the equal big sides. In other words, if these two, the small ones are equal to each other and the whole ones are equal to each other, so the remaining parts have to be equal to each other as well. So that actually probably would have been easier, straightforward. But again, the great thing about these things is that there's no, as long as all the steps you do are fine, that's fine. You don't get extra points for solving it in the minimum number of steps possible. So even though I solved it in a way that, and I proved it in a way that could have been done in a shorter way, the way we did it was fine. Okay, let us take a look at the last one, problem number 7. Given that DB is perpendicular to AC. So we're going to make this, we're going to make a little line over here to indicate this is perpendicular. And that B is the midpoint of AC, which means this is congruent to that. Prove that ABD, oh, you see, is congruent to CBD. This is an easy one. This is great. This is a lot easier than the one we just saw. Well, think about it. We've already got two of the angles. This, of course, if this is a 90-degree angle, this has to be a 90-degree angle. And we've got two sides, because it says that B is the midpoint of AC. These and this has to be equal. And this one we get on the the reflective, I think it's called the reflexive postulate, that things are equal to themselves. BD is equal to BD, and then we've got the two triangles on side, angle, side. Side, angle, and then a side, because they share a side. So this actually will be a very easy one. We'll solve this fairly quickly, hopefully. Let's go get our... Alright, there we go. We'll put this here with our diagram, and we will delete this. Let's make this a little smaller so that we can actually see it while we're doing it. Alright, so what are we given? We're given that DB is perpendicular to AC, because given. And B is the midpoint of AC, again, given. And that's all we're given. So, let's start with these two angles, ABD. Or let's start with the sides. AB, doesn't matter what order you do them, is equal to BC, because a midpoint, which is B, bisects a segment into two equal segments. Okay, that's simple enough. Then these two angles, ABD, angle ABD, and angle DBC, this one over here, are right angles, because a perpendicular lines, well, a perpendicular line, or lines really should be, perpendicular lines meet at right angles. Then we can say they're equal to each other because they're both right angles. So I'll just put an equal sign in the middle there, and we'll say right angles are equal to each other. And now we've got DB and DB. That's simple enough. DB equals DB, or BD, either way, because segments are equal to themselves. And now we've got side here, angle here, and side here, and then we can just say that triangle ABC is congruent to triangle CBD. And this we've got based on side angle side equals, or really perpendicular to side angle side. And we've proven it, and that's pretty much it. So the other ones were a little bit harder. This one's a little bit easier. Hopefully all of them are instructive. Now for homework 6, the good news is there are only 2 questions. These are all about angles and calculating them, and we've already done some of this anyway. But let's look at this, and this is a whole bunch of them. There's 28 of them here. This says A is parallel to B, which it shows in the diagram anyway. D is perpendicular to E. Where's line D and line E? Which means this is a 90-degree angle. Well, they're all 90-degree angles. All these 4 are 90-degree angles. Angle 28 is 40 degrees. And angle 8 is 60 degrees. And our task is to find all of the other angles. All right, well, listen, actually, this is very easy, actually, because once you get a few, they all start rolling in. Now, right away, just let's fill them in. Well, 60, these are vertical angles. 6 and 8 are vertical angles, so this has to be 60 as well. Now, 5 is You can get it because it's supplementary with 6, because it's on the same line, or you can get it because it's supplementary with 8. Either way, they have to equal up to 180. So this is 60, so this has to be 120. 7 also has to be 120 for any one of 3 different reasons. Either because it's supplementary with 8, it's on the same line, supplementary with 6, it's on the same line, or because it's equal to 5, because they're vertical angles. Okay, now let us look. Now we know that A and B are equal, which means that 9 and 7 are alternate interior angles on the same line, so we'll call that 120 as well. I'm just going to I'll write this down here. So I'll put this Alright, so we'll put this 120 over here as well. And then we've got 60s. Where do we put the 60s? Now the 60s, if you think about it, would have to be over here. And over here, there have to be a 62. I won't write them all in, but you can see fairly obvious. 12 has to be a 60, again, either because it's supplementary with 9, or because it's supplementary with 11, or because it's equal to 10. It's vertical angles. Okay, now we can't automatically get 1, 2, 3, 4, 13, 14, 15, and 16, but we can based on what we have down here. Let's see, what do we got? We got down here. We've got these are all 90 because these are all supplement. This is perpendicular. Line D and line E are perpendicular, so this is 90. Sorry, that's 90. That's 90. That's 90, and that's 90. Okay, this 40 means that 26 is also 40 because of verticals. 25, of course, is supplementary with either one, which means it's 140 because they have to equal up to 180 altogether. 27 is also 140 because it's either because it's supplementary with 28 or supplementary with 26 or equal to 25. Now 20 we can get too. 20 we can get because this triangle in here has to equal up to 180. This is 90, that's 40, that's 130 altogether. So 20 has to be the remaining 50. And because 20 is 50, 18 has to be 50 also. Because 18 is... okay, so, and because 18 and 20 are 50, 19 and 17 have to be supplementary, which means 17 has to be 130 and 19 has to be 130. Now, well, let's see, 12... This is 120. We got 11 is 120. 10, of course, is 60 because it's supplementary with 9 or because it's supplementary with 11. 12 has to be 60. Again, either because it's supplementary with 11, because it's supplementary with 9, or because it's equal to 10. Either way. Now, what about 15? Well, 18 is 50. 12 is 60, so that's 110. So there's 70 degrees left for 15. Because of the fact that it's a triangle, and triangles got to equal 180. 16, well, is supplementary with 15. Take away the 70, so it's 110 left. Then we've got 13, which has to be 70. Again, either because it is supplementary with 10 or because it is equal to 15. And 14, of course, has to be 110 also. Same reason. 4 is an alternate interior with 14. Because A and B are parallel. So 4 has to be 110. 2 has to be 110 because it's a vertical angle with 4. And 1 and 3 have to be 70 because they are supplementary with 4. And they're both supplementary with 4 and 2. And that's it. That's all our angles. There's a lot of them, but once you get going, it's a very simple problem. Just keep filling them in. A little time consuming, but hey, so what? Anyway, here we go. Here is another question, question number 2. Again, we got a whole lot of them over here, and we're going to fill them out one by one. Let me get a bigger one over here. I'm going to delete this and make this get one that's a little bit bigger here, in order to be able to fill them in a little bit better. Alright, let's make this as big as we can make it. There we go. Okay, let's get our pen out. Alright, angle number 1 is 90. Doesn't look like a 90-degree angle, but... Oh, I'm sorry. Well, determine whether each statement is true or false. Okay, well, before we even look at that, let's figure out what some of them are. This is perpendicular, so this we know is 90. Because this is 90, well, 9 has to be supplementary with this because it's on the same line, so 9 also has to be 90, which means 12 also has to be 90, which means that 11 and 10 together have to be 90. That doesn't help us much. Now, this is parallel with this. Notice these two lines are parallel. You got these little thingamabobs over here that signify that they're parallel. So 9 and 7 are alternate interiors, so that's 90. 8 is 90. What else do we got here? We got 11 and 2 have to be equal, of course. We don't know what they are yet, but 11 and 2 have to be equal because they are the base of an isosceles triangle, along with 5. I guess we know... Well, let's take a look at some of these and see if they make sense. Okay, for starters, let's look at number 1. Excuse me. 1 equals 90. Now, a 1, in order for 1 to equal 90, these lines would have to be perpendicular. Now, they don't look perpendicular, but that in itself doesn't mean anything. What does mean something, however, is that if this were perpendicular, if this were 90, then this would also have to be 90, because they're an ordered pair. On this line, the two lines would have to equal 90. Now, is that possible? I think the answer is that it's impossible, because if 2 and 11 are equal, which they are, they have to be, because they're bases of an isosceles. So if 2 was 90, then 11 would have to be 92. If 2 and 11 were both 90, that would equal up to 180. It wouldn't leave any degrees left for 5. 5 wouldn't be able to exist because 5 would be a 0-degree angle. 2 and 11, so 1 cannot equal 90. So we know that number 1 is incorrect. Because if 1 were 90 again, then 2 would have to be 90 because they're supplementary, which means 11 would have to be 90 because they're equal with 2, and that's not possible because you can't have a triangle with 2 right angles. You can't have a triangle with 2 90-degree angles, then the third one that wouldn't exist, wouldn't be anything left. How about number 1 equals 5 plus 11? Well, what does 1 equal? 1 is alternate interior with this. 1 looks like it, this is a transversal. This line over here cuts these two parallel lines, which means 1 is equal to 5 and 6 combined. And 6 is equal to 11, because if you notice, 6 and 11 are also alternate interiors. For the same reason. This is the transversal, these are the two parallel lines. So 1 is equal to 5 plus 6, and 6 is equal to 11. So that means really 1 is equal to 5 plus 11. So we'll give that a check mark. And we can explain why, because 1 is equal to 5 and 6 because they're alternate interiors, and 6 is equal to 11, so 1 by definition has to be equal to 5 plus 11. Okay, number 9 plus 10 is 2 times 5. Angle 5. Well, let's see. Number 1, let's take some of these lines out to make it a little less confusing. Okay, what do we have? We got number 9. Number 9, well, actually, I will put an X over here and a check over here. All right. Number 9, what did we figure out number 9? Number 9 is 90 degrees, plus number 10, which we don't know what it is, has to be double number 5. In other words, here's number 5, and here is number 9 and 10 combined. So does this big angle have to be double that angle? Not necessarily. I mean, it is true that this angle is alternate, that 4 and 5 combined equals 9 and 10 combined. Where's a different color? This whole angle has to equal this whole angle because they're alternate interiors. But that doesn't necessarily mean that it's double number 5. Yes, I don't see any inherent reason why 5 has to be equal. Basically, in order for 9 plus 10 to be 2 times 5, what essentially you'd be saying is that 4 is equal to 5. because double 5 would be 5 and 4, which is the thing that 9 and 10 combined are equal to. I don't see any inherent reason. I know that it looks like 6 is definitely equal to, well, 6 is equal to 11, and 11 is equal to 2. So, and 4 is equal to 2. So 4, 6, 11, and 12 all do have to be equal. 11 and 6 because of alternate interiors, 2 and 4 because of alternate interiors, and 11 and 2 because they're bases of a isosceles triangle. In fact, the truth is that the answer to that, this is actually no. I just realized that it's definitely not. And the reason why it's definitely not is because if 5 would be equal to 2 and 11, then it would be an equilateral triangle, not an isosceles triangle. It doesn't say it's an equilateral triangle, it just says it's isosceles. If it were equilateral, in other words, if this were also equal, then 5 would be equal to the others. Now, so if we know that 5 is not equal to 2 and 11, and we know that 2 is equal to 4, then we know that 5 is not equal to 4. Now, if 5 is not equal to 4, and this entire thing has to equal this entire thing, so we know that you cannot just double 5 in order to get the same as 9 and 10. So the answer is no. The last one is an easy one. 5 plus 6 equals 1. Well, 1 is an alternate interior with 5 and 6. So obviously the answer to that is yes. Next we have homework 7. Now homework 7 is where geometry kind of meets algebra a little bit. Things get a little bit more complicated in terms of the operational numbers. Maybe less complicated than some of the rules that we discussed earlier in proofs, but a little bit more complicated when it comes to numbers. So over here, question number 1 is find the area of the rhombus if WY is 30 centimeters. So over here, this of course is a rhombus. Now a rhombus has a few rules. First of all, the diagonals are perpendicular, which means that this has to be a right angle. The diagonals also bisect each other. That's true with all parallelograms. So if WY is 30, so then this has to be 15 and this part has to be 15. All the sides of a rhombus are equal. So for example, this is also x plus 9. And honestly, this is actually fairly easy. The problem here is that you have to figure out what x is. You know that the area of any parallelogram is base times the height, which is x plus 9 times x plus 9. But in order to figure out what that is, we need to figure out what x is. Now, the way I would figure out what x is by using the fact that you have these all 4 of these are right triangles. In fact, all 4 of these are right triangles with the exact same dimensions. So we can use the Pythagorean Theorem to figure out what x is. This, of course, wx is the hypotenuse because it's opposite the right angle. So what I would do is I would say the general Pythagorean theorem is a squared plus b squared equals c squared. So in this case, that would be x plus 6 squared plus 15 squared equals x plus 9 squared. There might be an easier way that I'm not thinking of right now, but you'd have to figure out, you need to figure out what x is, obviously, in order to know what the area is. So then this would have to multiply out into a fairly complex algebraic formula. X plus 6 is the same thing as x squared plus 12x plus 36, because it's x times x, which is x squared, plus 6x, which is 12x, plus 36. Basically, that's the same thing as saying x plus 6 times x plus 6. And if you remember FOIL, x times x is x squared, x times 6 is 6x, x times 6 is 6x, which equals 12x together, plus 36, plus 15 squared, which is 225, equals x squared, again, same thing. You have to make this into x plus 9 times x plus 9, which is x squared plus 18x plus 81. So when you combine, you got, well, the good news is, first let's combine. On this side, you've got x squared plus 12x plus 36 and 225, which is 261, equals x squared plus 18x plus 81. Okay. Now, the x squareds cancel out. If you wanted to get the numbers to one side and the letters to the other side. So you can subtract x squared from each side and subtract x squared from each side. So these cancel out. So the only thing you have left is x terms, which is 2x plus 261 equals 18x plus 81. So let's subtract 2x from this side and 2x from this side, and subtract 81 from this side and 81 from that side. So 261 minus 81 is 180, equals 18 minus 2, which is 16x. Divide each side by 16 to get x by itself, and you have 180 divided by 16. We should probably, let's use a calculator, okay? 180 divided by 16 gets you 11 1/4. So we've got x equals 11.25. So each of these sides is 11.25 plus 9, which is 20.25. So the area is 20.25 squared. And for that, again, we'll use our calculator. So we'll do 20.25 times 20.25, and the entire area is 410.06. So that looks like the whole area. Again, this was a hard one because of the fact that we had to use use a lot of algebra to figure out what the numbers were, but that's essentially what you would do. You got to somehow figure out what x is before you can answer a question like this. Question number 2 is a little bit easier here. Find the measures of the following angles of the rhombus shown. This is 2x minus 1. That's the angle CAB, it looks like. And it's this one here, and then you got x minus 1, which is here. Well, let's figure out the relationship between these two. Well, they want C, B, D. So the ones that they actually want are x. We'll call this angle A, little a, because that's what they ask for, and CAD. So they want little b here. Alright, so let's figure out what are the relationships between them. We know this is a rhombus, so first of all we know that these A and B are parallel, C and D are parallel. So the first thing, let's use the same thing that we did last time. Last question we used the fact that in a rhombus the diagonals bisect each other. So this becomes a right angle. Now, I'm thinking right here that can we get anything else? The answer is yes, that there are some other things we can figure out over here. And that's by virtue of the fact that the other side, all sides are parallel. AB, of course, is parallel to DC, and AD is parallel to BC. So right away, this is an alternate interior with this, so we'll call this also 2x minus 1. This angle has to be the same as that because of alternate interiors. X plus 1 has to be the same as over here. This also has to be x plus 1 up here. In other words, angle A, CBD, has to be whatever x plus 1 is, again because of alternate interiors. And of course, I just paused it for a little while and I was thinking about what to do over here, and then I realized there's a very, very simple solution that I was just overlooking, and that is that all of these triangles, for obvious reasons, this triangle, this triangle, this triangle, and this triangle, have to be congruent to each other for many different reasons. And there are many different reasons why they have to be congruent to each other. The first one is side angle side. This middle, of course, has to be a right angle for all four, and then this side has to be equal to this side because diagonals bisect each other, and that's true with all parallelograms. So that's true for here as well. So based on that, we could get all of these angles, all these little angles, based on corresponding parts. If this is 2x minus 1, and I'm sorry, yeah, all these have to be equal to each other. So if this is equal to 2x minus 1, and this is then this has to correspond to this side. So this would also be 2x minus 1, and this would also be x plus 1, and this would also be x plus 1, and this would also be 2x minus 1. In other words, all the angles that correspond to each other have to be the same. So based on that, we know that this plus this has to equal 90. Since this is 90, the other two combined also have to equal 90. So let's set up our basic equation saying 2x minus 1 plus x plus 1 equals 90. And to do that, we simply do 2x plus x is 3x. Negative 1 and plus 1 cancels out. So 3x is 90, so x is 30. So based on that, it looks like the 2x minus 1 angles would be 59. So these would all be, the 2x minus 1 angles would be 59, and the x plus 1 angles would be 31. So the CBD was in x plus 1 angles, that would be 31 degrees, and CAD would be a 2x minus 1 angle, would be 59 degrees. Okay, so let's take a look at question number 3 over here on homework 7. Okay, find the area of isosceles trapezoid below. Round to the nearest hundredth. Okay, well, that's easy. The area of an isosceles trapezoid. Now, the isosceles, of course, means that the two sides are equal. So this side would also be 4.3. So it's the average base times the height. Any quadrilateral is base times, like a parallelogram, rectangle, whatever, always base times height. So over here, for a trapezoid, you'd have to do the average base times the height. Now the height is, of course, no, actually the height is not 4.3. The diagonals are 4.3. So we have to figure out what the height is. We don't know exactly what the height is. So let's make two lines over here. Maybe we can figure it out using the Pythagorean Theorem. Well, if this is 10.4, then so in between these two lines, since these, I didn't draw them very well, but since if they're exactly up and down, of course, this would have to be 6 over here. And so because this was 10.4, there'd have to be 2.2 on either side. It'd have to be 4.4 left. So this would have to be 2.2, and this would have to be 2.2. So now let's figure out the height. And the height, we can use the Pythagorean Theorem. Since this is going straight down, this is a right angle. So we can use the Pythagorean Theorem, which of course is a squared plus b squared equals c squared. So a squared we'll call 2.2 squared plus b squared, which we don't know, equals 4.3 squared. 4.3 is the hypotenuse. So I'm just going to do on my little calculator here, 2.2 squared is 4.84. Plus b squared equals 4.3 squared is 18.49. Okay, so then we have to subtract the 4.84 from either side to isolate the b. And we've got b squared equals 13.65. So now we just need the square root of that, and we figured out what b is. Thankfully, we can round to the nearest hundredth. Okay, whoops. Let's see, 13.65. Square root of that is 3.69. We'll round to the nearest hundredth. So b equals 3.69. So now we know what the height is. We know that the height is 3.69. Now we need the average base. The average, well, the bottom base was 10.4 and the top base is 6. So to get the average, add them together, which is 16.4, divide by 2 in order to get the average. And that turns into 8.2. So the the average base is 8.2, and multiply them together. So we already had 3.69. Let's multiply it by 8.2, and we get 30.30, which means that the area of the base is 30.3, or 30.30 is the area of the entire isosceles trapezoid. Again, that's what we needed to do. We just needed to figure out the height, and you can always drop these altitudes down in order to be able to figure it out. Question number 4. Okay, determine if each statement is true if ABCD is a parallelogram and a rhombus. Okay, well, let's see. AD, which is this line, perpendicular to CB. That's true if it's a rhombus, but not necessarily true if it's a parallelogram. Remember, a parallelogram, diagonals bisect each other, but they are not necessarily perpendicular. So for a parallelogram, no. And for a rhombus, yes, because, I won't write it out, but because in a rhombus, diagonals are perpendicular to each other. Simple enough. Okay. AEC is congruent to BED. AEC, angle, AEC is perpendicular to AEB. Again, same thing. If this is a rhombus, if this is a parallelogram, well, not necessarily. They're supplementary to each other. They have to equal to 180, but they're not necessarily equal. But if it's a rhombus, the answer is yes, because they're 90. If they're both 90 degrees, if it's a rhombus, then obviously they have to be equal to each other. They have to be congruent to each other. AEC and AEB. Let's use a different color for C. AEC, that's this, and AE. I'm sorry, I made the mistake. So that was for number 3. What's BED? BED. Well, that of course is for both. So this actually answer was for this. For B, the answer is for both, because it doesn't really matter what the shape is. They're vertical angles. They're in any two angles that are crisscrossed by by two intersecting lines, opposite angles are vertical angles, which means that they're equal regardless. Doesn't matter what the shape is. Rhombus, parallelogram, nothing, trapezoid, circle, square, whatever, makes no difference. These two lines that are crisscrossing each other, the opposite angles have to be equal to each other. And finally, CEA, which is the same one, okay. And BEA, same thing. It's just really the same thing as the previous question. They just wrote them differently for some reason. That's kind of bizarre. But anyway, so that's a fairly simple question. So we can move on to the next question. And the next question is as follows. Similar type of question. Determine if each statement is true if PQRS is a rectangle or a square. All right, let us take a look. PR is perpendicular to SQ. Well, PR is not necessarily true with a rectangle. If it's a rectangle, it is not necessarily true. But if it's a square, it is, because remember, a square is a type of rhombus. So in a square, the diagonals are perpendicular with each other. So yes, if this is a square, this becomes a right angle. They all become right angles, because a square is a type of rhombus, and in a rhombus, diagonals are perpendicular to each other. Okay, STP and QTR. STP, that's this, and QTR, this. It's true regardless, again, same thing, because they're vertical angles, always going to be true. STP is 90 degrees. STP, again, only if it's a square, because diagonals are perpendicular. If it's a rhombus, if it is a rectangle, no. And, okay, QPT, okay, this angle, and equal SRT? And the answer, of course, is yes in both cases, because both rectangles and squares are types of parallelograms, which means that regardless of whether it's a rectangle or a square, this is parallel to this. Now, if this is parallel to this, then these two angles are alternate interior angles, and so therefore they are equal to each other. And that is all for homework number 7. Okay, homework number 8 is where we are now, and we are going to look at homework number 8. Now, this is chapter 6 in the book, and the first question, this is about similarity of triangles, and the first question is a question about the law of sines, or basically it's just a general rule regarding any triangle, and the rule in any triangle is the sine of A over A is the same ratio as the sine of B over B equals the sine of C over C. Now, in general, what sine is, it's really a trigonometric term, and the sine is the ratio of the opposite side of a triangle over the hypotenuse of a triangle. That, of course, only works with right triangles, because right triangles are the only ones that have hypotenuses. But in this case, of course, there is no hypotenuse. Nevertheless, the sine, which is a given number, it's something that you don't have to memorize, it's something that a calculator will tell you. I'm just going to take this off over here to give us a little bit more room to operate. But in general, a sine is a property of an angle. Sine of 30 degrees is a certain number. These are constant numbers that apply to all triangles. So let us take a look at what this says over here. ABC, angle A is 50 degrees, so I'll put a 50 degrees over here. A is 10, that's the length. C is 12, and now they want the rest. They want the angle B, they want angle C, and they want side B. Okay, they want, side B. Okay, so this should be a fairly simple example because it's the rule of sines. So the first thing we can do is we can get the rule of sines to get this one. Once we get this one, then B will follow. So let's take a look at how we would get the sine of C. Now, as the rule of sines is that sine of A is to A, as sine of C in this case, because we're looking for the angle of C, is to C. Well, okay, first of all, what is the sine of A? Well, A is 50 degrees. Okay, let's take a look at, let's take a calculator. Any kind of calculator will get this for you. So this is a particular calculator app that I have over here that will allow us to figure out the sine, and this is the sine of 50. So I'm going to put in 50, and over here I'm just going to click this, and the sine is 0.77. You can see I was practicing before I put on the video, so the 0.77 was already there. Anyway, the sine of A is 0.77, is to A, side A is 10, equals sine C, and we don't know what sine C is, so for the time being let's just leave it as x is to 12. And let's do this as we would an ordinary equation. 0.77 times 12, which is, well, let's do it on the calculator, times 12 is 9.19. You cross multiply whenever you have something like this. You just cross multiply. 10 times x is 10x equals 9.19. Divide each side by 10, and you have x equals 0.919. Now, in order to find out what angle that is, and obviously you would have to be given this on a test, you'd have to be given a chart. There are lots of different charts that this just one I randomly searched for and found the sine, cosine, tangent chart. And I looked up the 0.919. Looks like it's in between 66 degrees and 67 degrees. 67 degrees is 0.92. So I'm going to round it off. We can round it off. So angle C is about 67 degrees. I'm going to put that over here. I'm going to put that as 67 degrees. Well, now we can figure out what B is, right? That's pretty easy. We know that a triangle has to have 180 degrees altogether. So B and C together are 117, the 67 and 50, and that means, well, it's 180. B has to be 180 minus 17, excuse me, minus 117, which of course is 63. Okay, so now we've got two of the things they want, and the last thing they want is side B, and this we can use the ratio of sine B is to B as either, we can use A or C. I'm just going to use sine A because it's a smaller number. Maybe it'll be a little bit easier. But either way, so sine B, which we don't know what it is, so we're going to call, I'm sorry, sine B we do know what it is. So B is 63 degrees. So let's take out our calculator and find sine of 63 degrees is 0.89. So we'll put a 0.89 is to B, and we don't know what B is, so we'll just call it B. It's a variable. And the sine of A we already figured out before was 0.77, as to A was 10. So cross multiply 0.77 times B equals 0.89 times 10, which is 8.9. And then isolate B by dividing each side by 0.77. And let's whip out our little calculator once again. And so we've got 8.9 divided by 0.77, which is 11.56. So we've got B equals 11.56. And now we have solved the problem. We've gone, well, they say to round to the nearest tenth. So it's actually 11.6. So we'll call B 11.6. That's rounded to the nearest tenth. And now we've got all the answers that they were looking for. Question 2 is a little bit simpler, and it says that a map uses a scale of 1 centimeter for each 5 kilometers. Okay, let's write that down. Important to write these things down. 1 centimeter equals 5 kilometers. Looks like some sort of proportion problem. If a distance on the city map from city A to city B, okay, let's draw this on a map, city A to city B, is 17.5 centimeters. What's the actual difference in kilometers? Well, this is easy enough because it tells us what the ratio is. The ratio is, let's see, we've got 1 is to 5. In other words, 7 is the kilometer, the scale. Actually, well, this is, it's really 1 is to 1 centimeter. Okay, as long as we use the same, we can use the same ratios as long as we keep them the same. So 1 centimeter is to 5 kilometers, as 17.5 centimeters is to x kilometers. We don't know how many. Well, that's simple enough. Just, cross multiply. X times 1 is x. 5 times 17.5 is, I guess that's 87.5. Yeah, because 5 times 17 is 85. Okay, so that's 87.5. So the answer, of course, is that it's 87.5 kilometers. So we've got the first half. That's the easy part. Now let us look at the miles. They want the number of miles. There are 2.5 centimeters in an inch and 5,280 feet in a mile. So what's that ratio? So let's use the same basic scale as we used over here. We had 1 centimeter equals 5 kilometers. Well, there are more complicated ways to do this, but I'm just going to give you the simplest way. And it's a little bit of a memorization, but it's the kind of thing you might want to memorize anyway. And that is, in general, 1 mile is approximately 1.61 kilometers. That's generally the conversion. I guess you could round it off to 1.6. So if you have the number of kilometers and you want to figure out the number of miles, you simply divide by 1.61. So if we take out our calculator once again, and we take our number of kilometers, which was 87.5, and we will divide by 1.61. Again, if you forget the 1.61, you can use 1.6. It'll probably give you pretty close. 54.35. So the miles would be about 54.35 miles. The next question involves similar triangles. Now, images of triangles are similar, which means they don't have the same dimensions, but they have the same proportions. For example, in similar triangles, if one side is 3 and the corresponding side is 6, that means all the sides on the 6 will be double all the sides on the 3. So let's take a look at this example over here. Principle of a box camera is taking a picture is below. The rays of light from object AB, which is the tree over here, passing through opening L, form an inverted image AB. How far from the 30-foot tree, so we're going to say this tree is 30 feet high, how far from L must be placed to produce a 4-inch image. So this is 4 inches. This is actually 30 feet, and this is 4 inches. Of the film, if the film is 8 inches behind L. So this distance here, which is where the image is 8. Okay. Well, this simply looks like a proportion. Since these triangles are similar, the altitude of these images, in other words, the distance, will be similar as well, which means the ratio will be the same. So on this side, we don't know how long this is, so we'll call this x is to 30. Has to be similar to this side. The x is comparable to the 8, so we'll put the 8 over here, and this is a 4. Now, it's true this is feet and this is inches, but it doesn't really matter. It's the same proportion. So let's just, solve this equation. Very simple. Cross multiply. 4 times x is 4x. 8 times 30 is 240. Divide each side by 4, and x equals 60. So in other words, this has to be 60 feet away, which is, common sense. If this is going to be twice as far as the height is, well, then this also should be twice as far as the height is. So this one would be 60. Next question is question number 4. A vertical beam of searchlight, S, illuminates a cloud at P. An observer at Q stands 100 feet from S and measures the angle of elevation at 82 degrees. Okay. Now, first of all, this is a vertical beam. It's directly up. So what do we know about this? That has to be a right angle. It goes directly up at 90 degrees. Frankly, it really pretty much gives you everything you need to know. So what do they want? They want how high is the cloud? So they want from here to here. So that's x. This is actually a right triangle, so this really makes it extremely easy. They give you this angle here, and the ratio. So what are you looking for? The ratio is the opposite side over the adjacent side. The hypotenuse is not involved. Now, if you recall, there are 3 types of relationships. There's the sine of an angle is the opposite over the hypotenuse. The cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. SOHCAHTOA, as you may have remembered from high school. SOHCAHTOA. The sine is opposite over hypotenuse, cosine adjacent over hypotenuse, and tangent opposite over adjacent. So if we figure out what the tangent, which is the one we're going to use, the opposite over adjacent, because those are the 2 we have. We don't have the hypotenuse, so we can't use that. Well, let's just figure out what the tangent of 82 degrees is. That should be easy enough. Let's get out our calculator. So we'll put in 82 and click the tangent button. 7.12. Okay. So our 7.12 is the opposite, which is the x, over the adjacent, which is 100. Well, you can just stick this over 1, cross multiply, and you have, well, x times 1 is x, and 7.12 times 100 is 712. So the height of this cloud is 712 feet. And that's all there is to it. Just a regular tangent problem. Number 5 is an interesting one. This is again a similar triangle problem. We got two right triangles here on either side. They say a wire is strung between two posts as shown. What is the length of wire needed from A to B to C to D? All of these, here to here to here. What's the length of all this, cut up wire over here? Okay. Couple of things. First of all, this first triangle is really easy because this first triangle is simply the Pythagorean theorem. Now for this triangle, remember we have this and we have this, we just need the hypotenuse, a plus b plus c. Now I can tell you right now it's going to be 13 because I recognize this is a special type of right triangle. It's a 5, 12, 13 triangle. There are a few ratios where the hypotenuse comes out even. 3, 4, 5, 5, 12, 13, I think 8, 15, 17 is the other. But just to make sure, let's do it on paper. 5 squared plus 12 squared equals x squared because we're looking for this. 5 squared is 25. 12 squared is 144 equals x squared, which is 169 divided by x equals x squared. Take the square root of each side to isolate the x. Square root of 169 is 13. Okay, so this is 13. That part was easy. Now, if you notice, on this side, this triangle is similar to that triangle. Remember, to establish similarities of triangles, all you need is to have two angles that equal each other. Because if you have two angles that equal each other, you have to have the third angles that equal each other because they all have to equal up to 180 altogether. Now here it says that angle A equals angle D, here and here. Now these two angles are equal because this is perpendicular, so that's a right angle and that's a right angle. So they've got two equal angles. This is equal to this, and this is equal to this, so that by definition has to be equal to that. Now the sides of similar triangles are in proportion. So if we want this one, all we got to do is take this ratio to this as that is to that. So if we take 5 is to 13, as 7.5 is to x. See why that is? The ratios of similar triangles have to be in proportion. So this angle is comparable to that angle. I'm sorry, this side is comparable to that side, and the hypotenuse is the one that we're looking for in both cases. So let's multiply this out. 5 times x is of course 5x. 13 times 7.5. Well, let's see. 13 times 7 would be 91, and 13 times 8 would be 104, and so in between, I guess, would be 97.5, I think. And then we can divide each side by 5, of course, to isolate the x. And of course, x, well, let's see, 100 divided by 5 is 20, so 97.5 divided by 5 is 19.5. Okay, so this is 19.5. So we've got two of the components of the wire. Now all we need is this third component of the wire. Now this is a fairly complex one. I'm looking at it over here. The only way that I can think of to solve this, and there may be other ways that I'm missing over here, is to draw kind of an imaginary line over here in order to figure out BC using the side of a triangle. Because as of right now, it's really just a trapezoid. Not sure how to figure out the top of the trapezoid over there. So let's draw this imaginary line over here. Okay, now we've got a triangle here. And let's see what we can do to fill in the dimensions. Well, of course, common sense indicates that this has to be the same as this. This also has to be 15. And the reason is these are both altitudes. They both go straight up from the same line, so they have to, just keep going straight up. So this has to be 15. Now we got to figure out this whole thing over here. We know this little part down here is 12 from here to here. What about up here? Well, let's figure out what the whole side is. The whole side, this whole side, let's say from here all the way up here, we could figure out using the same proportion. From like this is to this as that is to that. So let's say 5 is to 12 as 7.5 is to x. Again, trying to figure out this whole thing. Same thing as we did before. 5 times x is 5x. 12 times 7.5, well, let's see, 10 times 7.5 is 75. 2 times 7.5 is 15, so that's 90 altogether. Again, you could do these on a calculator. There's no reason why you have to do it in your head. I just happen to want to do it in my head, but either way. And then divide by 5, and x equals 90 divided by 5, which is 18. So this whole thing, from C all the way to the bottom line over here, is 18, and we know that this area is 12, so this area up here has to be 6. And so now let's figure out how far it is from B to C, and for that we can use the Pythagorean theorem. And for the Pythagorean theorem, this is the hypotenuse. So again, we've got a squared plus b squared equals c squared. A squared is 6 squared. B squared is 15 squared equals x squared. This is not going to come out to a whole number, but anyway, it's 36 plus 215 equals x squared. So this comes to 251 equals x squared. So we need the square root of 251. Let's get out our calculator. And figure out the square root, which is going to be 15.84 approximately. So we'll call this 15.84. So if we add them all up, 13 plus 1584 is 28.84, and 28.84 plus the 19.5 is 48.30. I'm sorry, 48.34, of course. So altogether, we need approximately 48.34 the length to cover all this wire over here. Again, we had to just use the Pythagorean theorem a bunch of times. There might have been a simpler way to figure this out, but this was the easiest way that I could figure it out. Homework 9 is about circles, our first foray into the area of circles. And when it comes to circles, we are going to look at various rules, of course, that are relevant to this particular homework. And our first 4 questions, all of them, are relevant to this particular scenario. We've got a circle over here. We've got this is 50 degrees, that's 85 degrees, and we got a bunch of questions based on these. Now, C is not the center necessarily of the circle. A little confusing. It seems like, if it's a C, it's probably the center, but it's not the center. If it were to tell you that C is the center of the circle, then things would be a lot easier to deal with, but it doesn't say so, and therefore we can't assume anything. Okay, now before we even look at this, I'm going to, as we did earlier in the course with other things, I'm going to start filling in things that I know to be true. Well, this is 50. Now the rule is, in terms of a angle circumscribed on the edge of a circle, that it opens up to an arc that's double whatever this angle is. So this arc over here is going to be double whatever this angle is. Now we know that this is 50, so we know that this arc, in other words, the number of degrees from here to here in a circle, is 100 degrees. Now, because this angle opens up to the same arc, it also has to be 50 degrees. One of the rules is that any 2 angles that open up to the same arc have to be congruent to each other. Okay, that is fairly self-explanatory. So let's take a look at some of these questions over here. First of all, name 2 inscribed angles that intercept arc BD. Now, arc BD is here. Okay, that's now what 2 inscribed angles? Inscribed angles are angles that are on the end of the triangle, so it's really just this angle and this angle. So the 2 angles that I see are DAB. It's this one and this one, which is BED. Okay, I'm going to skip number 2 for the moment, just because that's a different kind of a question. Using only the points given, name all of the angles that intercept arc AE and indicate whether each angle is central, inscribed, or neither. Central is if it's in the center of the circle, if it's inscribed in the center of the circle. Inscribed is if it's on the end of the circle, or neither, of course, neither. Okay, arc AE is this. So There's angle ABE, that's this one, and that's inscribed. I'll just say INS for inscribed because it's on the edge of the circle over here. Then you've got EDA, which is inscribed. And then you've got this angle over here, which intercepts arc AE, ACE, which is neither because it's not an inscribed angle because it's not in the end of the circle, and it's not central because, again, C is not the center of the circle. In fact, C can't be the center of the circle, because if it were the center of the circle, then all the angles on either side of it would be exactly 180 degrees, whereas we know over here the arc is actually 185 degrees. So C actually cannot be the circle. Name two minor arcs and two major arcs and two semicircles on the circle. Well, the minor arcs are these two, AB and ED. Those are the smaller arcs. The bigger arcs are BD and AE. And semicircles, because C is not the center. If C were the center, then the semicircles would be AED and ABD. I'm looking at this one over here, angle EDC. I said I'd hold before. I'm just looking at it over here. I don't know if really there's a way to solve this. I mean, if C were the center of the circle, then it would be easy. If C were the center of the circle, EDC, well then, if C were the center of the circle, then this arc would have to be the same as this arc, because of course this angle is the same as this angle. And two central angles have to have the same the central angles have the same as arc measure, so this would be 100, and that would be 100, and that would be 100. And so because if this were a center, then this would be 100, that would be 100, that would be 100 degrees, which means that EDA would also be 50 degrees. Now, C is not the center of the circle, so honestly, I'm not 100% sure how to do this one here. I'll have to get back later on in order to, if I figure it out, I will let you know. But honestly, I'm not 100% sure that this is actually possible. But I'll certainly get back to you later in the recording if I do later on figure it out. Okay, but in any case, let us go to the next question, which is number 5, which I'm going to put up over here once again. Points A, B, and C are on circle O. Oh, by the way, in case you're wondering what happens if I can't figure something out, you're not going to get a question on an exam unless we test it and make sure that we have a readily accessible answer. So if you know the rules, you should be okay. In general, I think the exam questions aren't going to be as hard as the homework questions anyway. Okay, points A, B, and C are on circle O. Now, circle O means that the O is the center. That's an important thing to know. AC is 20 inches. Let's make this figure a little bigger in order to be able to draw on it. All right. Let's delete this one here. Let's delete them both and bring this circle here. Okay, good. Sorry about that. I'll just erase this. Okay. There we go. Now we've got point A, B, and C are in circle O, and the line, the diameter, AC, is 20 inches. So we'll say it's 20 from here to here. Okay. AC is 20 degrees. So I'm sorry. AOB is 120 degrees. Find the following. BC, so in other words, this line over here, measure angle BAC, this angle over here, and the area of the shaded region. Okay, let's start with what we know. Now, if this obviously is a straight line, so if this is 120, that has to be 60. And also, if this is 120 degrees, that means the arc of BC also has to be 120 degrees. Now, if the arc of AB has to be 120 because this is a central angle is the same as the arc. Now, what about this inscribed angle over here, ACB? Well, ACB has to also be 60, right? Because ACB is an inscribed angle, which is 1/2 of the arc that it intercepts. Now, so if this arc is 120, this has to be 60. Now, if this is 60 and this is 60, this also has to be 60 in order to equal up to 180. So this is actually an equilateral triangle. Now, so if it's an equilateral triangle, we could figure out all of the sides because, well, this was 20. Now, because this was 20, the distance from here to here has to be half of that. AC is a diameter, which means OC is the radius, which is half that. So that's 10. So that, of course, has to be 10, and that has to be 10 also. So we will say that BC, we figured out segment BC equals 10. Okay, so now we figured out part A. Now we need to figure out angle BAC. Okay, well that should be simple enough, right? If this is, there are many ways you can figure this out. First of all, this is a semicircle. ABC is a semicircle, which means if this is 120, then this arc has to be 60, because a semicircle has to have a total arc of 180. If this is 60, so this inscribed angle has to be half of that, so it has to be 30 degrees. And the other way to figure that out, of course, is that this central angle, BOC, is a central angle, and an inscribed angle that intersects the same arc as a central angle has to be 1/2 of its measure, for obvious reasons. If this is half of the arc that it intercepts, and this is the full arc that it intercepts, this has to be half of that. Either way, measure angle BAC, of course, has to be 30 degrees. And there are probably other ways you could figure that out also, but we don't really need to do that. Now the area of the shaded region. Okay, well this is a two-step process. The first thing we are going to want to do is figure out the entire area of the semicircle, and then subtract the area of these two triangles. Well, let's draw the whole diagram over again, because if we have all this busy stuff going on in the middle over here, that might confuse things a little bit. So let's get this thing again over here. Now, what's important here? Okay, let's draw in the information that we have that's going to be relevant to area. Now, the area of a circle in general is pi r squared. Okay, what's our radius? Well, remember, our radius was 10. And remember, this was an equilateral triangle, so this was 10 also. This was 10 also, but the point is that we are going to look at the radius, which is 10. So the area of the whole circle is 10 squared, which is 100 times pi. So we'll call it 100 pi, because the radius is 10, so radius squared is 100, so it's 100 pi. So the area of the semicircle, of this whole semicircle, which is going to be the most relevant part, is half of that, of course. So that's 50 pi. So essentially, the area of the shaded region is going to be 50 pi minus whatever these two triangles are. The entire semicircle minus what the areas of the two triangles are. Now, the area of a triangle is always the base times the height divided by 2. It's always the area of a triangle. So what's the height over here? Well, a little complicated, but we can figure it out. We're going to have to draw an altitude. The height of the triangle is always an altitude. So I'm going to draw an altitude down here and figure out what is the length of the altitude. I'll use a different color for that. Now, to figure out the length of the of the altitude, well, we have to, this side was 10, of course. This side was 5, because it's half of this. The altitude equilateral triangle bisects the base. So we can figure out this side, we'll call it S, using the Pythagorean theorem. Well, let's use it X. Let's call it X for the time being. Okay. So figuring out X using the Pythagorean theorem is a squared plus b squared equals c squared. In this case, we'll call side A 5. B is this side. We don't know what it is, so we'll call it X equals c squared, and that's the hypotenuse here, which is 10. So we have 25 plus x squared equals 100. Subtract 25 from each side. X squared equals 75. And so x equals the square root of 75. Let's use our calculator to get the square root of 75. Round it off, and we've got 8.66. Okay, we'll round it off to 8.66. That is the height. Okay, so figuring out the area of this triangle is base times height over 2. Now the base of the triangle was 10 times 8.66 divided by 2. Now 10 times 8.66 is 86.6 divided by 2. So the area of this triangle is 43.3. Okay, so that's the area of this triangle. 43.3. Now, the good part is that this is really the same thing. It's got the same base and the same height. The height is just the altitude. The height is from the highest point to the lowest point, which is the same thing for this circle as it is for this circle. In fact, the area of this is going to be the same as the area of this, because it's got the same base, which is this, which is 10, and it's got the same height, which is 8.66. So this is 43.3, and the other is also 43.3. You know what we could have done? I just realized rather than doing it as two separate triangles, we could have looked at it as one big triangle here, which has a base of 20 and a height of 8.66. And it would have been the same calculation overall. So our answer is 86.6, which is the area of the non-shaded region over here. So we've got 50 pi, which is the whole semicircle. Now let's figure out what 50 pi is. We'll round off pi to 3.14, so we'll say 3.14 times 50 equals 157. So it's 157 minus 86.6. And 157 minus 86.6. Really shouldn't need a calculator for it, but we have it open anyway. Why not use it? 70.4. So our answer is 70.4. So again, what we did was to figure out the area of the shaded region. We took the entire semicircle's area and subtracted whatever was not shaded, namely this big triangle or the two little triangles, either way you want to look at it. And question number 6 for homework 9. Points A, B, and P are on circle O. OA is 10 centimeters. Let's mark that in. Okay, OA is 10. And measure of the angle AOB is 80 degrees. Find the following. Arc AB, well that's easy, and encircle central angle has the same measure as its corresponding angle. The arc has the same measure as its corresponding angle, so the arc is of course 80 degrees, so that's obvious. We can just fill that in right away without even looking at anything else. Measure angle ABP, PB, excuse me. Okay. Now there is none, but we can always draw one. I don't see why not. Let's draw one. ABP. So let's start with A and go to B, and then go from B to P. Well, this is of course an inscribed angle, and an inscribed angle has the same measure as the as it has half the measure of the angle of the arc. So this, of course, would be half of that, which would be 40 degrees. So this would be 40 degrees. Those are the easy ones. The length of arc AB. Okay, a little bit of a circumference problem over here. Now, for that, we need to figure out the circumference of the entire circle, and then figure out the proportion, or the percentage, that arc AB is. The formula for circumference of a circle, the entire perimeter of the outside of a circle, is 2 pi r. Now, in this case, the radius is 10. It tells you specifically that OA is 8. I'm sorry, I wrote 10 over here, but OA is actually 8. So it would be 2 times pi r. The radius is 8, so 2 times 8 is 16, so c equals 16 pi. Okay, now let's figure out what the percentage of it is of... now this arc is 80 degrees out of 360. Now 80 divided by 360 reduces to 8 and 36, which reduces to 2 and 9. I guess 2 out of 9. So I think that reduces the same. Yeah, 8 and 36. If you divide by 4, it's 2. Divide by 4, it's 9. Okay, so it's basically 2/9 of the entire circle. So if you want to figure out what the circumference of AB is, what the arc AB is, it's 2/9 of the 16 pi. So it's 2/9 times 16 pi. Now if you multiply this out, 2/9 is the same thing as 2/9 times 16 pi is the same thing as, well, 2 times 16 is 32 over 9 times pi. So we can probably leave it as 32 pi over 9 or 32/9. If you want to actually get it into numbers, you can use a calculator. Estimating pi at 3.14, we'll say 32 times 3.14 divided by 9, and we're going to get about 11.16, give or take. So the whole circle is 16 pi, which is about 50 or so, and this is about 11.16, which is 2/9 of that. So that's in general how you figure out the length of an arc. You got to figure out what the circumference of the whole circle is, and then figure out what percentage the arc is of the whole circle, which is whatever number of degrees it is, divided by 360, because an entire circle, of course, has 360 degrees. Okay, let's take a look at homework number 10. More fun with circles, tangents, secants, all sorts of fun stuff like that. By way of review, we've got two different types of lines over here. We've got tangents and secants. A tangent is something that runs from an outside point of a circle alongside of the circle. Like J and PJ and PT are both tangents to this circle. They both hit the outside of a circle. In fact, it says so. JP and PT are tangent to circle O. J and T. JP is 10, PU or UP is 5, and PI is 6. And they want us to find, first of all, the relationships, in case you may not recall, the relationships between tangents and secants are that the tangent is the mean proportion between the outside component of the secant and the entire secant. These are secants. I don't know if I mentioned it, but PE is a secant, PR is a secant. A secant is any line that starts outside the circle and ends all the way on the other side of the circle. Basically, when you have a relationship between a tangent and a secant, like let's say, for example, PR and PJ, so in this case, PR would be to PJ, as PJ is to the small line PU or UP. Essentially, the tangent is the mean proportional in between. Like the mean proportional means on the bottom of and bottom of this fraction and top of that fraction, between the part outside the circle and the entire thing altogether. Okay, so let us take a look at how we would figure out all of these answers over here. PT. Now, PT is an easy one. The rule regarding fractions, I'm sorry, the rule regarding tangents is that all tangents, or really there can only be two tangents, and be, from one point to a circle, one can go here, one can go over here. If we had another line way back here, and we wanted to draw two tangents, then there could also be only two tangents from here to the circle. That one would look something like this, and the other would look something like this. There could be two tangents, and the point is the rule is very simple. The rule is that they're equal to each other. They have to be equal to each other by definition. Any 2 points from outside to the same circle have to be equal to each other. If you draw a few of them, you'll see why. It's fairly common sense. And so therefore, since pj is 10, pt also has to be 10. Easy enough. Okay. The radius of circle O. Now, the radius of circle O is obviously the distance from here to here, or from O to R, or from O to U. It's the same thing. Now, the only way to really figure that out is to figure out this entire thing, P-O-R, P-U-O-R, poor, or you can just call it P-R. And that's probably why they gave you U-P, because that's the only way to figure it out eventually. But the first thing we're going to need to figure out is the whole P-R. Now, remember, the general rule is that the tangent is the mean proportional on the bottom of one fraction and top of the other of the distance between the secant and this end of the circle and the secant and the other end of the circle. So essentially, UP would be as to PJ as PJ is to the entire thing, PR. I wrote it before with the UP and the PR reversed, but it makes no difference. It's the same thing. So let's fill this in. Then we can do this again relatively easy. UP is, of course, 5. PJ is 10 equals PJ, which is 10, divided by PR, which we don't know what it is yet, so we'll just call it X. Cross multiply. 5 times X is 5X equals 10 times 10, which is 100. Divide each side by 5. X equals 20. Okay. Now, if X equals 20, and this part of it is 5, PR is 20, and this part of it is 5, that means UR, the diameter, has to be 15, and which means each side of it has to be 7.5, because we're looking for the radius. This is 7.5, this is 7.5, that's 15, that gives you 20 altogether, so the radius of circle O is 7.5. Okay? And finally, we've got EI, and, we do it the same way, essentially. I'll use a different color, but you do it the same using the same proportion. Same exact thing. Again, this time, instead of UP, we're talking about IP is to, again, we can use the tangent, PJ. We could also use PT, which is the same, doesn't make a difference. PJ is to the entire secant, which is PE. Okay. Well, what's IP? Well, it tells us here that it's 6 is to 10 as 10 is to X. Well, 6 times X is 6X equals 100, and so X equals, looks like 16 and 2/3. Is that correct? Yes. 6 times 10 is 60. 36. Yes. So it's 16.66. Okay. Well, now they told you that PI was 6. I'm sorry. Well, that's the whole thing. Right. So EI would be this section. So if this section is 6, if the whole PA is 16.66, and this section is 6, so that leaves 10.66 left over here. So EI would be 10.66. And that's all for question number 1 on this homework. Question number 2. And let's see what we got here. Hopefully more fun stuff with circles. Oh, look, we have circles, secants, tangents, the whole 9 yards. Fantastic. Okay, RU is tangent to circle O as shown. Okay, arc ME is 118. Okay, degrees. Arc CE is 25 degrees. And MY, arc MY is 120 degrees. Find the following. RMU, this. MSC, this. MRY, this. Notice all 3 angles in the same triangle. And this. Okay, so these are actually fairly easy. The first one I see we can figure out right away is this one, MRY, which is one of the ones that we have to figure out over here. Now, the rule is for a secant, the angle of a secant, or two lines forming a secant, two secants forming an angle, and which in this case would be RM and RY, are one half of the difference between the arcs over here and over here. Just like, for example, on an inscribed angle, like EMU, it would be equal to this entire, it's one half of this arc, so two secants, it's one half of the difference between the arcs. So this angle MRY is one half of the difference between 120 and 25. So it's one half of 95, which is, of course, equal to 47.5. So we've got MRY. We've got MRY as 47.5 degrees. Let's write this in case this helps us at all. 47.5. Oh. Anyway. Okay, what else can we figure out here? Well, the next thing, and the next thing that's staring me right in the face over here, is that any tangent to any circle is going to be perpendicular to its diameter, to its radius. In other words, a radius or diameter is something that goes through the middle, which this line does. MOU goes right through the middle. And a tangent, like RU, this has to be perpendicular. This has to be at a 90-degree angle. Again, if you draw a few, you'll see why. It's fairly obvious. Any kind of a tangent that you draw to any circle, if you draw a line, let's do it in blue just to show you how it works. Let's draw a tangent on the other side, which I'll erase after we do it. If we draw a tangent here, which will look something like this, and then we draw a line from the middle to the tangent, it'll look something like this. You can see that's perpendicular. Anytime we draw a tangent to a circle and then draw a radius or diameter or a radius from the middle to the tangent, it's going to be perpendicular. So this has to be 90 degrees, of course. That also happens to be one of the ones that they asked. What is that? MUR? Yeah, so this is 90 degrees. Okay, now, well, this one, we can figure out just the fact that this is a triangle, right? I mean, this is 90, and that's 47.5, so this triangle, MUR, has to equal 180 degrees altogether. So 180 minus 90 is 90. 90 minus 47.5 is 42.5. So this has to be 42.5 in order for this triangle, MUR, to equal up to 180 altogether. So what RMU was 42.5. And then, the last one is MSC. Well, this is also part of a triangle. This triangle is MSR, this whole triangle in the middle here, basically. That would be the same thing. Well, this is 42.5, and that's 47.5. And so that those two add up together to 90, of course. No, I made a mistake. You see what mistake I made? I'm not going to tape over this because pause it and see if you can see the mistake that I made. And then I'll have to tell you the mistake that I made, and then we'll have to do it over. The mistake that I made in figuring out this was that this is 47.5, but that's not the whole angle. When I looked at it, I thought that was the whole angle. When I say MRU, the three angles are this, which is 90. That's true. The whole angle is not 47.5. The whole angle is going to be more than 47.5 because the 47.5 is only MRY, which is this component of the angle. It doesn't apply to this component of the angle. So we'll have to figure it out in a different way. Okay, so looking at this for a couple of minutes while I had it turned off, I think I figured it out. I mean, again, sometimes you got to look at these things for a few minutes. It may take a little while. Okay, looking at this over here. Well, this is a semicircle. MOU is of course a diameter, and therefore this MEC CU, this whole thing is a semicircle. Now, if this is 118 degrees and this is 25, the arc of a semicircle, of course, has to be 180 altogether. So 118 and 25 is 143, and 143, that leaves 37 left. So I guess that would have to be 37 degrees, the CU arc. Yeah, 37 and 25 is 62, 62, and 118 is 180. Exactly. Okay, so this has to be 37. So we know that. Now, if this has to be 37, then we can figure out these two angles. Remember, these two angles have to be equal because they're vertical angles. And those two angles each have to be the average of the intersecting arcs. In other words, these two arcs together have to be the same as the two angles together. So, if we, for example, take the average of 120 plus 37, so 120 plus 37 is 157, 157, let's see, 157 divided by 2 is 78.5. So this has to be 78.5. This has to be 78.5. In other words, the total measure of the two angles, the two vertical angles, have to equal the combined measure of the arcs. So, okay, now looks like we can figure out the triangle SRU. Well, this is 90. That's 78.5. That adds up to 168.5, which means there's only 11.5 degrees left. 11.5 degrees is this angle over here, which means the total measure of this, and I'll use a different color. Again, there may be simpler ways to figure it out. I may be using the most complicated way for everything, but so be it, whatever works. So this angle, MRU, which is actually one of the ones that we had to figure out. No, I'm sorry, we had to figure out RMU. So, okay, anyway. So MRU is 47.5 plus 11.5, which is 59. Okay. So if this is 59, and that's 90, 90 and 59 is 149, that leaves 31 degrees left over here. 31 degrees for this angle. 31 plus 59 is 90, plus 90 is 180. Okay, so at least we got RMU. RMU we got is 31 degrees. Now we need MSC, which is this angle over here. We'll stay with green. Okay, well this isn't so bad. So MSC, we've got the other two angles in this triangle. We've got the 31 over here. We've got the 47.5 over here. So these two angles, this one and this one, add up to 78.5. The entire thing has to be 180. So we'll subtract and get 101.5. So it looks like this angle has to be 101.5. So we have all our answers. Again, I may not be doing this the most efficient way, but just, keep, as long as you know the rules, and there aren't that many of them. It seems like there are a lot, but there's really only, 4 or 5 rules that apply to each of these situations. And somehow, if you just keep filling in as many numbers as possible, sooner or later you're gonna figure out everything. Just out of curiosity, if we wanted to know, this arc, well, this arc we could figure out 2 different ways. We could figure it out. That 101.5 are these two angles, and this angle is going to have to be the 101.5 times 2 is 203. So 203 has to equal 118, which is this arc, plus whatever this arc is. So it would be 203 minus 118. So that's 85. This has to be 85. And now just to check it, let's make sure that... Well, anyway, let's not worry about that. We got let's look at we got plenty of actual problems to do. So let's look at problem number 3 here. And question number 3 for this homework. We've got a clock over here. The minute hand on a clock sweeps out 20 minutes. Now, 20 minutes, before we even look at that, 20 minutes is, of course, 1/3 of an hour. Now, 1/3 of an hour, 1/3 of a 360-degree circle means 120 degrees. We might not need that. We might need that. We'll see. I don't know. So if this, of course, is 120 degrees, and this is also, of course, 1/3 of the entire circle. If the hand is 4 centimeters long, this is also 4, they're both hands, they're both radii, so they're both 4 centimeters long. What is the shaded area? I guess we can assume B is the center because that's where the hands start on a clock, at the center. So this is 4 and that's 4. What is the shaded area swept out by the hand showing the figure? So it seems to me very simple. What we're going to need to do is first figure out this entire area and then subtract the triangle here. Okay? Okay, I'm still looking at this, and I spent a couple of minutes looking at it, trying to figure out what to do over here. And again, I think I figured out a way to solve it, although again, with my usual disclaimer, I will say that there might be a much simpler way that I'm just not thinking of. The way that I think of, basically, we need what AC is, and we need to figure out what AC is, and of course we also need to figure out what the altitude is, because we need to figure out the area of the triangle. We need to figure out the whole area over here of this semicircle, and then we need to subtract what the area of the triangle is. So first, before we even do that, let's figure out the area of the semicircle. That's the easy part. Now, the area of the entire circle is, the area of a circle is pi r squared, as we know. The radius is 4, so the area of the entire circle is 16, 4 squared times pi. So that means the area of the third of a circle, the area of this whole area over here, 1/3, that is 1/3 of a circle, because that sweeps out 20 minutes, which is 1/3 of the clock. So the area of the 1/3 of the circle is 16 divided by 3 pi, which is, we'll call it 16/3 pi, or we can call it 5 1/3 times pi. Okay, either way, fine. Let's put that on the back burner over here, because now we know what the whole area is over here. Now we have to figure out what the area of this triangle is, so that we could subtract it in order to get the area of the shaded region. Now, to do that, the only thing that I see offhand that would actually work is to draw an altitude here. Just draw it straight down here. This is an isosceles triangle, so the altitude bisects them. This triangle, of course, is equal to that triangle. And now we can use a little trigonometry to figure out this side over here. Now, this, of course, entire is 120 degrees because it's the same as this angle. So half of it would be 60 degrees over here. This has to be 60 by definition, because this line splits the two angles. It bisects the angle. It goes straight down the middle over here. This entire thing is 120, so each one is 60. Now, if we have this as 60 degrees and this as 4, so we can use a little trigonometry to figure out this and this. Let's whip out our calculator over here, and so this is the hypotenuse of the triangle, and this is the adjacent side of the hypotenuse. That's what we're looking for. We're looking for this angle over here. So we're going to use the cosine. Remember, cosine is SOHCAHTOA. See, cosine is the adjacent side over the hypotenuse. So in this case, the adjacent side, which is what we're looking for as x, will be, let's see, the cosine. Now, what's the cosine of 60? Well, let's use our calculator to figure that out. We could use a chart or a calculator. So we'll say 60 degrees and put in a cosine, which is 0.5. Actually, I knew that, but all right. So the cosine is 0.5. So we'll say 0.5 equals the adjacent which is x, divided the hypotenuse, which is 4. Now, if you cross multiply, very simple, it clearly has to be 2, because 0.5 is a half, so this side also has to be a half. If you want to cross multiply it, you'd be x times 1, because this is really 0.5 over 1 over x. So x equals 0.5 times 4, which is 2. So x is 2. So I'm going to change this x into a 2. That's the altitude of the triangle, of this triangle over here. And now let's figure out what this is over here in order to figure out what the entire AC is. And we can do that two different ways. Number one, we can use the 60 and we can use the sine to figure out the opposite over hypotenuse, or we could just simply use the Pythagorean theorem, because this is a right triangle, of course. So let's use the a squared plus b squared equals c squared, and a squared is, let's say, 2 squared plus b squared is x squared. We don't know what that is, equals 4 squared. So that's 4 plus x squared equals 16. That means x squared equals 12, and x equals the square root of 12. Now, so this is the square root of 12, which means the entire base, the entire AC, is 2 times the square root of 12, because this bisects congruent triangles. So this, of course, has to be twice times the square root of 12. So base times height. The area of a triangle is always 1/2 of the base times height. So in this case, the area of the triangle is 1/2 of the base, which is 2 times square root of 12, times the height, which is 2. So the area equals, well, 2 times 2 is 4, half of 2 is 2. So really, I mean, we can take a half and 2 and just cross them out, because half of 2 is just plain 1. So the answer is 2 times the square root of 12. So let's get, in terms of numbers, up here we've got 5 1/3 pi, and down here we've got 2 times the square root of 12. So let's figure out what both of them are. I'll use even a different color. Let's whip out our calculator here. And, okay. So let's do the 5 1/3 pi first. 5.33333, whatever, times, and pi will round off to 3.14. So we're going to round it off to 16.75. So we've got 16.75 being the area of the entire third of a circle, this whole area over here. And then we're going to subtract the area of the triangle. And the area of the triangle was 2 root 12. So let's do that. Let's clear it again. Take 12 and take the square root of 12. About approximately 3.46. Again, we're rounding it off. Times 2 is 6.93. So we're going to subtract 6.93, and that equals 9.82, I believe. Okay. So that is the area. The area of the shaded region is 9.82, because the area of the whole third of a circle is 16.75. The area of the triangle is 6.93. Subtract them and you got 9.82, which is the area of the shaded region. Homework number 11. Okay, here we got. We're going to start graphing for the next few homeworks. Let's draw ourselves a graph over here, and this is covered more in the algebra class as well. But let's draw an x-axis and a y-axis. I'm going to do this the first time. After that, maybe I'll take some shortcuts. But what you always want to do whenever you draw a graph is to have an x-axis and a y-axis, put arrows on each side to make sure that you realize the graph goes forever, or the axes go forever in each direction. Label the vertical axis the y-axis and the horizontal axis the x-axis. And of course, that's positive 1, positive 2, positive 3, all the way to positive infinity. This is the y-axis positive, this is the y-axis negatives, and this is the x-axis negatives. Okay, points A and B have coordinates -3 and 5, and 4 and -3. Plot the points. Okay, that should be easy enough. -3, 5 is -1, 2, 3. That's the x value. In an ordered pair, the first value is always the x value. 5 is 1, 2, 3, 4, 5. So let us put this over here, and that's A. And then B is 4, -3, 1, 2, 3, 4, -1, 2, 3, and that's B. And now they want, interestingly enough, the line segment. How long is this line segment? Okay, so we've done A, and let's do C first. C is the easy one, so that we'll just do first, and then we'll have to get into something a little bit more complex when we look for how long line AB is. So for the midpoint, just take the average. Take what's in the middle. We got our 2 points, -3 and 5, and over here we have 4 and -3. Just take the average of the x and the average of the y. The midpoint, well, the average of -3 and 4 is positive 0.5, I believe. If you add them up, 4 and -3 is positive 1 divided by 2. That's how you get the average. And 5 and -3, well, 5 minus 3 is 2. And so it's positive 1. The average between 5 and -3 is positive 1. If we want to plot the midpoint, we can do that by going 0.5, which is here, and positive 1, which is right about over here. Maybe my line wasn't precise, but that's about the midpoint. And if you're looking at it with the naked eye, you can tell that it's pretty close. Again, my drawing of the line might not have been 100% precise, but that is, I believe, the correct answer. Okay, so let us now take a look at the second part of the problem, and that's find AB. Now for AB, we're not going to need the chart, because this is simply an application of the distance formula. So I am going to take the chart out. In fact, I'm going to take this stuff out too, because we already got our answers. So what I'm going to do is the distance formula. Now the distance formula, it's just really something you got to memorize. And that is the distance is the square root of the change in x squared plus the change in y squared. Change means the difference. I'm going to use the delta, which is the triangle, which means change in y squared. So let's take our x's. Well, our x's are, let's say, -3 and 5. I'm sorry, -3 and 4. Those are our x's. Our y's are 5 and -3. So you can go either direction. You can say this minus this or this minus this, as long as you do it consistently in both. So let's take the bottom minus the top for the difference in x. So the difference in x is 4 minus -3, which is 7. 7 squared. Okay, the difference in y is -3 minus 5, which is -8, which is going to be the same thing as positive 8, because any positive number squared is the same as the negative number squared. So we'll call it -3 minus 5, which is -8 squared. So the distance is 49. Square root of 49 plus -8 squared is 64. Now 49 plus 64 looks like 113. So the distance is the square root of 113. If you wanted to figure it out, what it would be, what the distance would be approximately, you can again just put in, okay. Put in 113 and get the square root, and it's about 10.63. So the distance between those two things those 2 points that we plotted on the graph is about 10.63 boxes. You can usually leave it as a square root of 113 because that is an irrational number. So that is question number 1 for homework 11. Question number 2, let's see what we got over here. The coordinates of two vertices of an equilateral triangle, two ends of an equilateral, or two of the 3 points that end in equilateral triangle are 1, 1. Let's plot 1, 1, which is over here. And the next one is 5, 1, which is over here. We want an equilateral triangle, which means the distance between here and here has to be the same distance as the distance to the third vertex. Now, actually, there are really 2 different places the vertex can be. It can be somewhere up here, where it can be, this of course is 4, so this has to be 4, and this has to be 4, or you can do it down here and put the vertex somewhere around here, and you can make an equilateral triangle either way. I think it's a little simpler to make it, to move it this way. So the vertex is going to have to be somewhere up here. The problem is you don't know exactly where it is right now. You can't just put it up here, 4 spots up. In other words, this is 1, 2, 3, 4 over. It doesn't go all the way up 4 spots, because if we put this up 4 spots, I mean, just to show you what it would look like if we drew a triangle, clearly it would not be, let me draw this with straight lines, clearly it would not be an equilateral triangle. I mean, you can see right away that the bottom side is not nearly as long as the top 2 sides. It's an isosceles triangle, but it's not an equilateral triangle. So we have to realize that this third point, which we'll make in yellow since we don't know exactly where it is, has to be somewhere on this third line, because there has to be equidistant from both sides, but we don't know where on this third line it can be. So we're going to have to figure out, we don't know how far. We're going to have to figure out some sort of a line from here to here. We don't know. Well, let's use a different color because you can't see yellow. It's going to have to be somewhere from here to somewhere around here. We don't know exactly where it is. Let's just leave it somewhere around there, and it's going to have to be somewhere around here. Now, there is a way to figure out the length of this. We don't know exactly how high it's going to be, but there is a way to figure out the length. Okay, sorry about that. I left the recording running for a little bit, so you just basically saw nothing for about a half a minute or so. Hopefully you hung on and are still with me. If you're not still with me, well then there's kind of no point in discussing it, is there? Okay, let's draw axes over here. Okay, we want to make sure we can get a -10. Okay, now, first of all, it asks you whether PQ is perpendicular to QR. So let's draw PQ, obviously. P is -5, 6. That's -1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay. 7, -2. 1, 2, 3, 4, 5, 6, 7. 1, 2. Okay. And 1, -10. 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So they want to know if PQ, oh, let's label them. This was P. This was Q. And this was R. So PQ and QR. Let's draw the lines. PQ and QR. Okay, now do they look perpendicular? They look pretty close to perpendicular. I guess you can't really tell by the naked eye. I'm trying to look, at a diagonal. It looks slightly off perpendicular to me, but all right, anyway. But we don't have to look, fortunately. There's a very easy way to figure out whether they're perpendicular, and that is whether their slopes are negative reciprocals of each other. Parallel lines have the slopes that are the same as each other, and perpendicular lines have slopes that are negative reciprocals of each other. Now, the way to figure out a slope is always the change in y divided by the change in x. So let's figure out the slope of PQ. Now, change in y means, where are PQ? PQ is negative 5, 6, and 7, negative 2. So the change in y, we'll call the second y minus the first y. Change in y is negative 2 minus 6. Again, this one minus this one. That's the change. You can do it either direction as long as you're consistent with both. And it's doing the x and the y divided by the change in x. This should be the change in x, which is 7 minus negative 5. 7 minus negative 5 is the same thing as 7 plus 5. That's the same as negative 2 minus 6 is negative 8. 7 plus 5 is 12. Negative 8, 12 is the same thing as reduces to negative 2 over 3. Okay, so that is the slope of PQ. Now let's try the slope of QR. Okay, well, let's do the same thing. Change in y, negative 10 minus negative 2, which is the same thing as negative 10 plus 2. Again, minus negative 2, so that's plus 2. And 1 minus 7 is on the bottom. 1 minus 7. And let's see what this is. Negative 10 plus 2 is negative 8. 1 minus 7 is negative 6. Now, negative 8 over 6 comes out to positive 4 over 3. So this is negative 2 over 3. This is positive 4 over 3. So they are not perpendicular with each other because they do not have negative reciprocals. If this would have been positive 2/3, and this would have been positive 3/2, it would have had to, in order for them to be perpendicular, if this was negative 2 over 3, this would have had to have been positive 3 over 2. It's close. 4 over 3 is close to 3 over 2, but not quite good enough. And so they're not exactly perpendicular, and I think if you've been staring at this the whole time, you might have also seen that they're not exactly perpendicular. See, this seems to come in at a slightly sharper angle. This seems to be a little bit less than 90 degrees. But anyway, we figured it out mathematically, so we don't really have to rely on the naked eye, thank goodness. Question number 4. Okay. First of all, let's draw our coordinates over here. I think for all these, maybe I should have something saved with a nice graph with good coordinates. Again, you really should put arrows in x, y, but we'll dispense with that for the time being. All right. So we've got a township has corners with the coordinates 0, 0. So that's at the origin. That's right in the middle over here. 7, 0. 1, 2, 3, 4, 5, 6, 7, 0. 7, 5. 1, 2, 3, 4, 5. Okay. And 2, 5. 1, 2, 1, 2, 3, 4, 5. Okay, it looks like a trapezoid here. So let's draw the trapezoid. Use a different color to draw the trapezoid of the town. Okay. All right, so what do they want? Remember that they're 5,280 feet in a mile, and that 1 acre is 43,560 feet. What is the nearest? Find the area of the township to the nearest tenth of an acre. Okay, so this is in miles, I presume. Yes, they're given in miles. It says so in the question. Given in miles. So first thing we got to do is figure out the area of a trapezoid. Now, the area of a trapezoid is always the average base times the height. Is the base really the base 1 plus base 2 over 2 times the height. That just means the average base. This is the longer base. This is the shorter base. This, of course, is the height. So that's easy enough. what is the average base? Well, this base is 7. You just count them: 1, 2, 3, 4, 5, 6, 7. This base is 5, so that's 7 plus 5 over 2. The height is, of course, 1, 2, 3, 4, 5. So the area is 7 plus 5, which is 12, over 2, which is 6, times 5 equals 30. So the area is 30 square miles. Okay, so now we have to think quickly about or it doesn't have to be quickly, but we have to think about the number of square feet there are in a mile. Now, a mile is 5,280 feet, which means a mile is actually 5,280 times 5,280 square feet. Square feet is two directions. If a mile is 5,280 feet that way and 5,280 feet that way, the total number of square feet in a mile is actually 5,280 squared, or times 5,280. So that's actually the number of square feet in a mile. That's a lot. 27, looks like 27,878,400. That makes sense. Sounds like a lot, but there really are a lot of square feet in a mile, over almost 28 million square feet in a mile. And how many square feet an acre? 43,560. So we can divide this, which is the number of square feet in a mile, divided by this. Well, actually, there's 30. There's 30 square miles. I'm sorry. So this is just 1 square mile. This is how many square feet there are in 1 square mile. Our trapezoid, our township, has an area of 30 square miles. So we're going to multiply that by 30. And this is how many square feet there are in the township, which is 836,352,000. Okay, again, makes sense. Townships have a lot of square feet. Now we can divide this by this number to get the number of acres, because that's the number of square feet in an acre. So let us use the division, divided by 43,560, and it gets you 19,200 acres. Okay, it says it gives us to the nearest tenth of an acre, but I don't really see the need to round off because it tells you that there's altogether 19,200 acres in the town. Okay, question number 5. I think that's the last question on the homework for homework 11. Now, here we got 4 vertices, 4 corners, and they ask us to show that it is a rhombus. First of all, we have to know how to figure out the distances, and then we have to know what the rules for a rhombus are. We don't even, technically speaking, need to draw this on a graph. We could figure it out using the distance formula, but it's a lot easier to visualize, and I think a lot easier to do if you draw it on the graph. So A is negative 2, 12. Negative 2 is 1, 2. 12 is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You know, I'm going to have to redo the coordinates to make this work a little bit better. So let me redraw the coordinates a little bit lower so that we can get everything in the chart. Alright, not the coordinates, the axes. We're going to draw a little bit differently. Okay, no problem. Okay, negative 2, 12. Point A, negative 2, 1, 2. Positive 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way at the top. Okay, this is A. Now, B, negative 1, 1. Negative 1, negative 1, excuse me. 1, negative 1. That's B. 10, negative 8. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Negative 1, 2, 3, 4, 5, 6, 7, 8. All the way down here. And our last one is 9, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. All right. Let us draw the connectors for this quadrilateral, which we are going to have to prove is a rhombus. Okay. Looks like a rhombus. Feels like a rhombus. Quacks like a rhombus. It probably is a rhombus. All right, anyway. So what's the rule for a rhombus? Well, the rule for the rhombus is very simple. They all got to be equal to each other. All sides have to be equal to each other. Which means, that's right, folks, we got to do the distance formula 4 times. This was C, of course, and this was D. So, well, let's write the distance formula up here. D equals the square root of change in x squared plus change in y squared. In case you're wondering how this formula is derived, it's really just a takeoff on the Pythagorean Theorem. I'm not going to go into it now. I can do that in a different section, or you can just take my word for it, but this is really just a derivation of the Pythagorean Theorem. Okay, so let's take a look at AB. Let's try AB. AB is the distance is the change in y, excuse me, square root of the change in x. Now the change in x squared, now the change in x is -1 minus -2, so that's just plain -1, or 1, doesn't matter which one, we can do -1 squared, plus the change in y. Now the change in y you can see right away is going to be 13, -1 minus 12 is -13, so we'll say, again, it doesn't matter whether it's negative or positive, -13 squared. That means the distance is -1 squared, which is 1, plus -13 squared, which is 169, and our distance is the square root of 170. That's okay. It's nothing wrong with having an irrational number as your distance. We just got to make sure that all the other segments are the same. So this is the square root of 170. Well, okay, let's take a look at BC. Distance equals the square root of change in x squared. -8 minus -1 is -7. So we'll say -7 squared. Plus 10 minus -1, which is 10 plus 1, which is 11 squared. Distance equals the -7, which is 49, plus 11 squared, which is 121. 49 plus 121, sure enough, is 170. So distance is square root of 170. That's so far so good. Square root of 170. Let's figure out the other two, and I'm going to have to take this out, or this area out over here, because otherwise we're not going to have any room. So let's apply the distance formula 2 more times. Hopefully we'll get the square root of 170 both times, and then we will have our proof. So now let's try CD, which is this line segment. Distance equals the square root of the change in x. 9 minus 10, -1, okay. -1 squared, plus 5 minus -8, or positive 5 plus 8, which is 13 squared. You might see a pattern. That's the same basic numbers we had when we did AB, which makes sense because this is parallel and equal to AB. So that's 1 plus 13 squared is 169. Distance is the square root of 170. Congratulations. And finally, we've got DA, or AD, which we have to compare this to that. Okay, let's start with the change in x. 9 minus -2, which is -11. I'm sorry, positive 11 minus -2 is positive 11 squared. And then the change in y is 5 minus 12, which is -7 squared. 11 squared is 121. Plus -7 squared is 49. Again, you may recall those numbers from BC because, again, AD is parallel and equal to that, and your distance is the square root of 170. That makes this the square root of 170. We've done all 4 distance formulas. All 4 sides are the same, and because all 4 sides are the same, that makes it a rhombus. Now, if they would have also asked us to prove that it's not a square, because a square is really just a type of rhombus, and so we could. Thankfully, it didn't ask us that. If it did, it would just be a little extra work, but it would be fairly simple. All we'd have to do is prove that one of the pairs of segments are not perpendicular to each other. In a square, all the sides are perpendicular to each other. We would just have to figure out the slopes of, let's say, AD and AB, or AB and BC, and prove that they're not negative reciprocals of each other. And if you look at this with the naked eye, I think it's very apparent that this is not a square. But that's okay. It didn't tell us that it didn't tell us to prove that it's a non-square rhombus. It just told us to prove that it's a rhombus, and we did. So congratulations to us. And now we are on to homework 12. Okay, let's take a look at this. We're not going to use the actual axes for all of these things. Write the equation of the line that goes through 4, and is perpendicular to the line with the equation of 4x minus 2y plus 5 equals 0. Now the thing is, in order to get any equation, the first thing we have to do is get it into y equals mx plus b form. And the way to do that is to get the y on one side and the numbers on the other. So the easiest way to get y on one side is to solve for y is to add 2y to each side. If we do that, then we get rid of the y from that side, and we add y to the other side. I'm going to put the y in the left. It doesn't really matter that much, but I'm going to put the y in the left. So 2y equals whatever's left over, 4x plus 5. Now we can isolate y by dividing every term by 2. So we've got y equals 4 divided by 2 is 2x, plus 5 divided by 2, which we'll leave as 5 halves. So that's this equation. So this equation is y equals 2x plus 5 halves, or plus 2.5. You can write it like that also, it's fine. Now, we want the equation that runs through the lines of 5 and negative 4 and is perpendicular. Now, perpendicular means that it has a negative reciprocal slope. Negative reciprocal in this case, negative 2. 2 is really 2 over 1, so the negative reciprocal is negative 1 over 2. So the slope of our new line is going to be negative 1 over 2. That's what we know so far. But what we don't know is the y-intercept of our new line. We know the y-intercept of the old line, but we don't know the y-intercept of our new line. Our new line is going to be y equals negative 1/2 x, because we know the slope. The slope is whatever's next to the x, plus b, but we don't know what the y-intercept is. And so let us go ahead and figure that out. And the way we can figure it out is by using this point, by plugging in our y values and x values as is indicated in this equation. So we had y equals negative 1/2 x plus b. Let's use the 5 and the 4. Instead of the y, we'll use the 4 because that's our y value. Equals negative 1/2 times 5 because that's our x value, plus b. And this you'd solve like any other equation. 4 equals, well, 1 times 5, so it's negative 5 halves plus b. Add 5 halves from each side. We'll call it 2.5 to make it look a little bit more normal. And so 4 plus 2.5 is 6.5 equals b, which means that the final form of our equation, this was the form, so we've got y equals negative 1/2 x, or negative 0.5 x would also be fine, plus 6.5. This is the equation of a line that is parallel to this one, because this one had a slope of 2, and it had a y-intercept of 6.5. Okay, next question. Very similar, maybe even slightly easier than the one that we just did. We've got an equation, and it's 2y equals negative 3x plus 4. And our first issue is to rewrite in y equals mx plus b form. To do that, all you really need to do is Solve for y. Now here, all you need to do for y is just divide by 2 to isolate the y. When you do that to 1, you got to do it to the other terms here. So you've got y equals negative 3 halves. And let's call this 1.5. It just looks a little bit more normal. Negative 1.5x, that's the same thing as negative 3 halves x, plus 4 divided by 2, which is 2. So we've already done a. We've written it in y equals mx plus b form. That was easy. What's the slope? Well, the slope is always the coefficient of the x. Whatever's next to the x is always the slope. And so the slope is 1.5, or 3 halves. Now they want us to show that 2, negative 1 is on the line. The only way to figure out whether a particular point is on the line is to plug it into the y and x values and see if it works. So the equation for the line was y equals 1.5x plus 2. Let's plug in these values and see if they work. For y, we'll change to negative 1, 1.5. X will change to 2, plus 2. And of course, I made a mistake before, which hopefully you caught. This was negative. Remember, there was a negative sign over here that I forgot somehow. So this was actually y equals negative 1.5x plus 2 was the equation. And the slope was negative 1.5. Very important. I messed that up, but that's okay. We can look back. I was wondering why it wasn't working as soon as I saw this equation. And then I looked back and realized, oh, that's right. I forgot that little negative sign, that pesky little negative sign over there. So let's see if this works. And this, I think, is going to work. Negative 1. Well, negative 1.5 times 2. Well, 1.5 times 2 is 3. So it's negative 3 plus 2, and of course, negative 3 plus 2 is negative 1. So negative 1 equals negative 1, which means it works, and therefore, the line 2, negative 1 is on the line because it works. Okay, next question. Question number 3. We got 2 equations, and they ask us to solve the systems of equations. Now, you can do it algebraically. You can solve an equation that way, but in our example, we're going to try to do it graphically. The way to solve equations graphically is to plot them both on a graph and see where they meet. Oh, that should be pretty easy. Let's take the first one. The first one, let's make that red. So we've got y equals 2/3 x plus 5. Now the way to graph an equation, put a little chart here where you got x and y, and put whatever the x value, y is 2/3 x plus 5, okay? And let's take 3 values for x. Let's take 0, 1, 2, why not? Okay, so 2/3 times 0 is 0, plus 5. So in this case, y is 5. In the second one, it's 2/3 times 1, which is 2/3, plus 5, which is 5 2/3. And the third one is 2 times 2/3, which is 4/3, or 1 1/3, plus 5, which is 6 1/3. Let's plot this line. 0, 5, 1, 2, 3, 4, 5. And then 1, 5 2/3, which would be something like this. And then the next one will be 6 1/3. Let us draw a line that represents this equation. Okay, and then let's draw it the opposite way also. Okay, I think this is about right. So this is our first equation. Now let's graph our second equation. I'm going to delete this. I hope when we get to our second equation, it's going to crisscross. Better. Anyway. So what's our second one? Our second one, we got 2x minus 3y minus 3 equals 0. Well, I'm not going to write it again. We have it right there anyway. Now, here we do have to solve. The first one already started in y equals mx plus b form. Here, sorry, we'd like to get it in y equals mx plus b form first. Now, to get it in y equals mx plus b form, get the y's by themselves. So you can do this term, add 3y to each side. Again, I'm going to put the y term on the left. So 3y equals 2x minus 3. Divide by 3 to isolate the y. Divide that by 3, divide that by 3. And you've got y equals 2/3 x minus 1. This doesn't make any sense. They're never going to solve. They're parallel to each other. They got the same slope. If they have the same slope, they're parallel. If they're parallel, they're never going to intersect, ever. And in case you don't believe me, let's do it. I only got the problem from the book. It's not my fault. Well, maybe it is for not... But anyway, this is not going to work. You got x and y. Let's see. First of all, let's just make sure that we didn't make any... Okay, let's see over here. We'll do this again. This was 2/3 minus 1. 2/3 x minus 1. Again, let's do 0, 1, 2. 2/3 times 0 is 0. That's a negative 1. 2/3 times 1 is 2/3 minus 1, which is negative 1/3. And the third one is 2/3 times 2 is 4/3 minus 1, which is 1/3. All right, let's put this. 0, negative 1 is here. 1, negative 1/3 is here. 2 and 1/3 is here. And when we draw this line, you can see it is going to be parallel to the red line up there. All right. Anyway, so you can see these two lines are parallel, unless I'm making a mistake. And again, I'm just looking at the two slopes. This one is clearly, the two slopes are both 2/3. And for this one, again, yeah, it's 2/3. They're both, okay, well, we got the two lines. You can see they're parallel to each other because they have the same slopes. Any two lines with the same slopes are parallel to each other. This is not solvable. There's no way, even if we tried to do it algebraically, there would be no way to solve this because these two lines don't meet at all, ever. Okay, question number 4. State the equation of a... State the equation of a circle in general form which has a center of 5, 3 and a radius of 9. Now the standard form for an equation with the circle is, if the circle is in the origin, then it's just x squared plus y squared equals whatever. You know, for example, if it's 9 or 25, or it could be anything. And in this kind of a scenario, the radius is simply the square root of this. You know, the square root of whatever that number is, which of course would be 3. So an equation like this would simply be a circle with the center at the origin and a radius of 3. You know, if I'll show you, rather than graphing, which is very hard to actually graph a circle if you have my artistry skills, I'll use this, which is a website that graphs stuff for you. And let me go. So this, which is x squared plus y squared equals 9, you can see what it looks like. It's basically a circle. I mean, it is a circle with the center at the origin, 0, 0, and the radius is 3. If I changed this to 25, for example, then the radius would simply change to, whoops, I did 15. If I did 25, then it would simply change to a radius of 5. You know, the radius would be, it would go 5, the circle would go 5 in each direction. Now, if the center is not at the origin, then what you need to do is put it in this form, which I'm going to write over here. X minus whatever, something called h, I'll tell you what that is, plus x minus k equals the radius squared, where the h is the x value of the center, and k is the y value of the center. So in our example here, that would be x minus the x value, which is 5, x minus 5 squared, plus x minus k, which is x minus negative 3, because k is the y value, so which is negative 3, which turns into plus 3 squared, equals the radius squared. What's the radius? Well, it says the radius is 9, so 9 times 9 is 81. So this is the equation for a circle in general form with a center of 5, 3, and a radius of 9. In order to test it out, let's write it in here. What's our what did we get over here? Let's make sure that we get the correct equation here. We had, let's say, x minus 5 squared plus, this should be y, whoops, okay, y plus 3. Let me correct that. Before we go, let's change this to y. I'll just erase it, and then I'll take out my little pen over here and make this into a y. Fine, okay. And then it equals 81. If we got this correct, then the radius should be 9, and the center should be 5 and 3. And let's see if that works. 5 and negative 3. And let's take a look over here. Let's see, where is the center? The center is right here at 5, negative 3, right here. That looks about right. Should be right over here, the center. That's right. And the radius, whoops, the radius should be 9. Let me drag these down so you can see the whole circle over here. The radius should be 9, and that seems about right also. In fact, let's see where the center is. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, it's 9 in every direction. So this is the correct equation. The next one is a hard one. The next one we have to use a method called completing the square. Hopefully you're familiar with that from the algebra class. If not, well, then you need to kind of relearn that a little bit at this point. We got like a really weird form of an equation over here, and they ask us to change it into a circle form. Well, okay. We're going to have to convert this into a form that we saw before. You know, x minus h squared times x minus, or y, did it again, y minus k squared equals the radius squared. Okay. In order to do that, we're going to have to set up two perfect squares, one with the x and one with the y. I'll keep the 11 and the 0 because those are the constants. But we're going to want an x squared here and a y squared here. And what other x terms do we have? We've got an x squared term here. We've got a plus 2x term over here. And for y, we've got a y squared term and a minus 4y. Either way, we're going to need to add a last term to complete the square to get it into this kind of a form, to get it into an x minus h squared form. If you don't recall, the way to complete a square, the way to get this down into a single term that is squared, is to put a number over here that is going to force the trinomial to be broken down into two binomials that are the same. And the way to do this is to take half of this value, whatever it is, and square it and put that number over here. So now half of 2 is of course 1. 1 squared is 1, so we can put the 1 over here. Let's do that over here. Again, let's say half of negative 4 is negative 2. Negative 4 squared, negative 2 squared is positive 4. So let's put a positive 4 over there. I'll take out the underlined to avoid confusing you. And we'll put a positive 4 over there. Now the reason why this will complete the square is that x squared plus 2x plus 1 is the same as x plus 1 times x plus 1. That's the whole point of completing the square. X times x is x squared, plus another x is 2x plus 1. That's, when you FOIL it out. So this is really the same thing as x plus 1 times x plus 1. This, of course, is the same thing as y minus 2 times y minus 2. So that's really going to be the purpose. But before we even get there, you can't just add these numbers out of the blue. I mean, the great thing about algebra is you can do anything you want to one side, but you got to do the same thing to the other side. So we added a 1 in here, okay? So that means we got to add a 1 to this side. We added a 4 over here, so we got to add a 4 to this side. So let's look at the next step. This is the same thing as x plus 1 times x plus 1, so we're going to rewrite this as x plus 1 squared. This is the same thing as y minus 2 times y minus 2. So we're going to put, I'm sorry, I left out a plus sign here. So we'll put the plus sign in there. Y minus 2 times y, okay, so this is y minus 2 times y minus 2, which is y minus 2 squared, minus 11 equals 0 plus 1 plus 4, which is 5. Now, we still don't have it quite finished yet. We almost have it there, but we need to get rid of this constant over here. And now, so we can do that by adding 11 to this side and adding 11 to that side. And now we've got x plus 1 squared plus y minus 2 squared equals 16. Now we've got it in the appropriate form. What is the center? Well, the center is the negative value over here. Remember, this is x minus h. So it's whatever the negative value over here is. So the center is negative 1, and whatever the negative value here, and the negative of negative 2 is positive 2. So the center should be negative 1, positive 2, and the radius. Well, the radius, remember, this is r squared, so it's the square root of whatever this is. So the radius is the square root of 16, which is, of course, 4. In order to make sure that we're correct, I am going to bring up my equation grapher over here. And let's see, what should we write over here? Well, we can use this, or we can even go one step further. Oh, let's use this. X plus 1 squared, y minus 2 squared, and that equals 16. Of course, our radius is going to be 4. This should be 2. I don't know why I wrote 3, but that should be 2. And our circle is going to be, here's our circle. Our center, we said, was negative 1, 2. Negative 1, 2 right here. It looks about right. Looks exactly right, as a matter of fact. And the radius should be 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Yeah, it works. Let's write the whole thing over again, by the way, the whole equation, and see if it comes out to the same one. It better come out to the same one, but let's make 100% sure. Let's write the whole thing. X squared was plus y squared plus 2x minus 4y minus 11 equals 0. And when I press go, it better stay the same because this is it's really, we just kind of alternated it and moved it around a little bit. When I press go, bang, stayed the same. See, that the number of seconds it took to complete changed a little bit, but it stayed the exact same thing because all we did was reformulate the equation by completing the square. Key with this is you gotta expand it and make sure to put a number over here that's going to cause it to be the same binomial times itself. So that is how we got that answer. And let's take a look at the last question for this homework, which actually is a very easy one, so I'm just going to zip through it here. Write the standard form of the equation shown below. Well, where is the center over here? Well, the center is the origin. Center's right in the middle, so we don't even have to worry about minus h and minus k or whatever it is. So we know right away that it's simply x squared plus y squared. There's no minus h or minus k because the center is right smack dab in the middle. Equals what? Well, it's the radius squared. What is the radius? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Obviously, the radius is 5. 5 times 5 is 25. And that is the whole standard form for the circle shown here. Okay, homework 13. ABCD is a rectangle. This is we're going to do transcriptions, transformations, things like that. Things that are actually a little less complicated than a lot of things we've done so far. But let's get to it. ABCD is a rectangle, which means opposite sides are equal, etc. Point E is the point of intersection of the diagonals. Now, in a rectangle, diagonals bisect each other. Diagonals are equal. Well, diagonals are not necessarily perpendicular, but they are equal and they do bisect each other. Determine which of the transformations, A to D, can be used to map the rectangle onto itself. In other words, which change will leave everything the way it is. A reflection with respect to BD. Okay? If BD reflects is where every point, it's like kind of mirror, where every point is the same on either side of it. So reflection of the entire image with respect to BD, BD is this line over here. Well, let's figure it out. If you flipped everything, if you translated everything from one to another, would they be equal? Well, let's take all the individual elements. If you take BC and reflect it over BD, let's draw the reflection line over here just to make it nice and clear what we're reflecting. This, well, let's not use black. Let's use red to make it a little bit more clear. This is the reflection line. Well, let's see. If you reflect BC over BD, what's going to happen? Well, is it going to go all the way to AD? Not really. If you flip it over this line, it's going to look something like this. I mean, the reflection, let's draw BC for a second. Again, let's use a different color. If we have BC over here, if we want to reflect it in AB, well, again, assuming this was a mirror, it wouldn't go all the way down here. What it would actually look is something like this. It would look like a line that's the same length as BC, but it would be reflected over in this direction. So already, I think that a reflection in BD is not going to work. So we are going to, so not A. What about B? A rotation around E of 90 degrees. Rotation is just kind of turn it counterclockwise. Now that's definitely not going to work. In fact, we can actually test it using Microsoft Paint over here, the program that I'm using. A rotation around E of 90 degrees. I'm going to rotate it by 90 degrees, and it looks like this. It went on its head. So let me rotate it back. Okay. It was standing upwards. It was standing vertically. It wasn't sitting horizontally. So that doesn't work. Reflection with respect to AD. Well, okay. If you flip the entire thing over AD, it would be the same size and the same shape, but it would be on the other side. In other words, it would be somewhere over here. The entire shape would have kind of reversed over here, so that wouldn't work. D, on the other hand, looks like it would work. Rotate around E of 180 degrees, which means one full revolution. If you take it and you flip it entirely around once, it's going to look the same. In fact, so that actually will work. Let's rotate it 180 degrees and see what happens. Well, basically looks the same as it did before. I mean, these words up here look different, but the shape itself looks the exact same. You flip it around, and so that actually will work. So D is the only one that I see so far. And E, which of these transformations can be used to prove that diagonals are congruent? And of course the answer is E, because when you rotation around E of 180 degrees, you see the diagonals won't have changed at all. Even though the diagonals will be in the opposite, instead of AC going to the right and DB going to the left, it will be, let me rotate it. It will be CA going to the right and BD going to the right and DB going to the left and AC going to the right, but it's all the same. So because of that, that shows that the diagonals will look the same regardless of which one's in which position, showing that they are equal to each other, showing that they're congruent. The next question isn't really much about math. It's really just about stating, what seems to be fairly obvious. A map of a state includes county lines, excuse me. A new map of a particular county is to be drawn using the state maps. That the county map is 4 times the area of the county on the state map as shown. Explain how this might be accomplished. Well, one possibility is just simply to increase all the dimensions by 4. Multiply ED by 4, DC by 4, BC by 4. This is what's called a dilation. A dilation is when you change everything by the same factor. So that's simply just multiply all the dimensions over here, each line segment by 4, and eventually you're going to have the area. Actually, I'm sorry, check that. If the area you want 4 times, so the distances only have to increase double. I think we discussed this in a previous homework. So because a square area is a square measurement, whereas length is a linear measurement, is one-dimensional as opposed to two-dimensional. So if you want to increase it 4 times, you really only have to make it twice as big. So really increase by 2. Increase AB by 2, BC by 2, CD by 2, ED. Just make everything 2 times the size that it was, and you should have 4 times the area. I mean, just to give you an example, if we had a box that was 1 by 1, and then you have another box that's 2 by 2, instead of making it 1 by 1, we'll make it 2 by 2. Let's see, is this approximately double in each direction? Well, let's see. Let's assume that this is about double. Well, this is not perfect. Let's make a red box that's approximately double the size. Okay, I think this is somewhat similar to double. In other words, this is twice as wide and twice as tall, but it's going to be 4 times as big. 1 box, 2 box, 3 box, 4 box, because you have to square. If you for example, if you have, let's say, a 2 by 2, and you made something like this. So if you increased this by 2 by the number of boxes, in other words, if you doubled this, if you had instead of 2 boxes in this direction, you had 4 boxes in this direction and 4 boxes in this direction, instead of it being 4 boxes, it would actually be 16. So in other words, if I doubled this and I made it go, twice as long this way and twice as long that way, and you can see the red shape. It's maybe 4 wide as opposed to 2 wide and 4 tall as opposed to 2 tall, but instead of being 4 boxes, it would be enough room for 16 boxes altogether. Hopefully that's fairly self-explanatory. Okay, question number 3. Now here I see everything is going to be in the positive domain, so I'm going to draw my axes. This is a transformation problem, so I'm going to draw my axes way down here and put the whole thing in a positive quadrant, and even so I might not have enough room to get everything in. Let's make this the x-axis and this the y-axis. It doesn't really matter where you draw the coordinates, I'm just drawing it because I want to have enough room to plot all the relevant points over here. Okay. In fact, this time I'll even put the arrows, arrow here, arrow here, arrow here, arrow here. This is the y-axis, this is the x-axis. Okay, great. Now we've got a triangle here, ABC. ABC has vertices 0, 0, so we'll put A over here. 6, 0, 1, 2, 3, 4, 5, 6 here, so we'll put B here. And C, which is 2, 8. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. So this is C. Let's draw our triangle. Alright. Okay, so we've got our triangle, our red triangle here. Fine. Okay, good. Now they want to sketch ABC and its image A prime B prime C prime onto the size transformation with center A. With center A simply means that you're using that as the starting point of the dilation. It doesn't mean that A is the center of the triangle. Obviously, A is not the center of the first triangle, and it's not going to be the center of the last triangle. It's the basis upon which you're measuring everything else. So, based on that, since it's the origin, that's actually very convenient. We can say, okay, so A prime is still 0, 0 because that's the center of dilation. So we're going to say we're going to maybe color it orange also and make it an A prime. Now B prime, we have a scale factor of 2.5, so we can multiply the x value and the y value by 2.5. Now the y value is still 0. The x value turns to 15, right? 6 times 2.5 is 15, so 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And the y value, so really this is b prime. So a prime was still 0, 0, the dilation of A. B prime, the dilation of B, was 15, 0. The dilation of C is 2.5 times to each one. So 2.5 times 2 is 5, and 2.5 times 8 is 20. So it would be 5 and 20. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Well, we almost got there. You see why I wanted to make a big one. Anyway, so we'll put it up here. We'll guesstimate it. Now let's draw our circle. I'm sorry, our triangle, of course. Oops. Okay. There we go. The base of the triangle is going to run through here to the end over here, and then the last line, the longest, or this side of the triangle is going to be this. Now notice, of course, that the lines to the bigger triangles ran right through the lines of the smaller triangles, but it's a bigger triangle. It's a similar triangle, by the way. It's got all the same angles. In case you're curious about how we prove that it has all the same angles, well, angle A and angle A prime are the same point, so obviously those are the same angles. And well, I don't know. They just are the same angles. So they all have the same number of degrees. But of course, this one, the orange one, is 2.5 times as long in every direction. Okay, so that's the coordinates of A prime, B prime, which we already wrote over here. If a point has coordinates A, B, what are the coordinates under its image under the size transformation? And of course, that would be exactly what we used for a 2.5. Times dilation, so that would be 2.5a and 2.5b. Our last homework question for homework 13 has the unfortunate task of having the word similitude in it. Similitude, of course, just means not necessarily similar, but the way in which one shape, in this context, can be transformed into the other. Now, here we got two examples over here, a 3, 4, 5 triangle and a 12, 16. We don't even need to, but we can easily figure out what A prime, B prime is. That's the hypotenuse. We can use the Pythagorean Theorem. There are many different ways. I'll tell you right now that this is going to have to be 20. And the reason why it has to be 20 is very simple. First of all, it's what's known as a 3-4-5 triangle. You know, when you use the Pythagorean theorem, if the hypotenuse is 5 and the other two are 3 and can be 3 and 4. So 12 and 16 are divisible into 3 and 4. So 20 is also, it's the same ratio basically. 3, 4, 5 is the same ratio as 12, 16, 20. Anyway, but that's not the point. The point they ask over here, what is the similitude that takes ABC into A prime, B prime, C prime? Well, so we have to describe it as completely as possible. The first thing it's doing is it's transforming. It's reflecting in a line down the middle over here. So one thing I might do, and there are different ways you can describe this. There may not be a perfect way or an imperfect way to describe it, but I may put a line over here, and maybe I'll call this line L. And so the first thing I will say is that reflect ABC, triangle ABC, in line L. And that will give you A prime, C prime, B prime, C prime, but it'll still be a 3, 4, 5. You know, it's just flipping over, and it's the opposite, but it's still 3, 4, 5 as opposed to 12, 15. 12, 16, 20. So the second thing you need to do is you need to dilate, using a size transformation. Sorry, I'm not writing very neatly. Of 3. Everything's being multiplied by 3. The 3 is being, oh, one second, no, that didn't work, I'm sorry. I mean, the second part of it is true. Everything is being multiplied by 3. Or by 4, actually, not 3. What am I talking about? By 4. 3 turns into 12, 4 into 16, and 5 into 20. But the problem is that that doesn't work because you see what, oh, okay, so you see what's happening over here. If it would just be flipped, then the 4 should be over here, because the 4 should be opposite the 16. So it's not actually being reflected. Now that I take a look at it over here, it's not really being just reflected in line L. What is actually happening? We don't even really need line L to reflect it anymore, because what's actually happening, it looks like it's being, before it's being dilated, or after it's being dilated, it's being rotated. So let me get my pen back over here. Before, it's actually being rotated because the 3 is going to the bottom, so it's kind of being rotated. It's being stood up, so it's being rotated counterclockwise 90 degrees. This is kind of being stood up. Is there any way that I can illustrate my point? Rotate 90 degrees left. See? Look at that. You see that? Oh, perfect. Isn't Microsoft great? Anyway, see, now it looks more like this. I'm rotating it 90 degrees to the left, or 90 degrees counterclockwise, because now I'm standing it up to the point where the 4 is comparable to the 16, the 3 is comparable to the 12, and the 5 is comparable to the 20. Before I did that, the 4 was not, and if I just flipped it over, if I rotated it, it wouldn't work. I'll illustrate that. If I just rotated it by flipping it horizontal, which would be flipping it over an angle, see, this wouldn't work. You can see that the 4 is on the side where, on what should be the smallest side, and the 3 is on what should be the bigger leg, so that wouldn't work. So the only thing that would work is if I rotate it 90 degrees to the left. Now you can see that it's comparable to this shape with just a dilation of 3. So I'm going to change this, and I'm going to say that this, we can rotate triangle ABC 90 degrees counterclockwise. I guess we can also say to the left, but I think counterclockwise is slightly more correct, because it's only left if you're looking at the screen. If you're on the screen looking out, then it would be right. But alright, anyway, so that is counterclockwise. I guess the same thing is true with clockwise and counterclockwise. But anyway, so we'll call it counterclockwise.